Doing the detection.
This is this cable.
Yeah.
Let me grab my...
Oh, wait. There it is.
Okay, I see you now.
All right.
No idea why that took so long.
That's good.
Okay.
And
So you
I
should be able to
will
see it
go
back
ahead
there.
and put you on screen then.
All right, cool. All right. Hello, everyone. Hello. Good morning. Woo! Welcome to Bang Bang Con 2024. Oh my gosh. Just making sure we're good on live stream and everything before I begin. Audio, video, captions. All good. All right. Welcome, everybody. My name is Erdi Seidel. I use he, him, or they, them pronouns, and I'm one of the organizers here at Bang Bang Con. It is so amazing to see everyone here in person. And what an amazing venue. Shout out to my fellow organizer, Lindsay Cooper, who works here and got us this courtyard for free. Thank you so much. Thank you to University of California for letting us use it for free also. Yeah, woo. This conference almost didn't happen. The organizers got together and we said, should we even do Bang Bang Con this year? It has been 10 years since we started, and we all have a lot more responsibilities and things. And we just decided, yeah, you know, let's do it. We're going to do one more. Here we are. Going to go out with a bang bang. And one deep thank you to a person named Lee Pepper, who is attending online. Lee was our administrative assistant. We hired them this year, and without them, this certainly would not have happened. So thank you, Lee. Round of applause for Lee. I know none of you know them, or few of you know them, but they really helped put this together. I also just have a couple more thank yous before we begin. There are so many people to thank, so many people helped put this together, but we just want to really shout out Addie Weinstein and Melissa Baker, who really helped with event logistics, like renting all of these chairs. Tony Sabala leads the facilities team, has answered all of our questions. Bob Burns and his colleagues made the internet access work, which is, details are up here. We have not one but two Wi-Fis for you. Juan Perez on audio. Thank you. Yeah, catering team, everybody who helped put this together. Round of applause for everybody who made this happen. Three more. Cindy Backman and the Confreaks team is running the live stream. Mira by Night is transcribing everything I say over here. And Dave Dunning with Legend Theatrical is making this beautiful video wall happen. So thank you to those folks as well. All right. Yeah, we are doing this, and it is also in part because of all of you. Thank you especially to folks who sponsored, who stepped up when we put out a call that said, hey, we are $20,000 in the hole. Somehow our budgeting didn't work out like we thought it would. And folks really stepped up, and we appreciate everyone. Pay what you want tickets. We were able to do pay what you want. We were able to do captioning, live streaming, all of that stuff because of those folks. I'll shout out the specific sponsors later, but you know who you are. Thank you. Thank you so much. I will talk more about Bang Bang Con in general later, but for now, some very quick venue orientation. Ready? Yeah. Bathrooms are in the back there. You'll see a sign just through the glass doors. We've marked both of them as gender neutral, and they're back there. You'll see the signs. What's next? Wi-Fi. Yes, UCSC guest or Bang Bang Con. Ask any organizer if you can't get in. UCSC guest does not have a password, so use that one. What's next? Furniture. Try not to move the furniture around too much. Yeah, but feel free to sit anywhere. What's next is food. We have breakfast over here. Thank you, UCSC Catering. There's coffee over there. And then we will also have the boxed lunches appearing around lunchtime. Organizers. There are 4 of us this year, and we are in this color of shirt. If anything bad or good happens, you can come and find us. Our organizer team is over here. Sarah, Lindsay, Joshua, and myself, Erdy. All right, and, okay, we also, I didn't make something spin for it, but we also have Unconferencing later today. We'll talk a little bit more about that later. Basically, it's an unscheduled conference time where people can sign up to give little talks or presentations that aren't on the official, track. Sign-ups and organization for that. If you have an idea for an Unconference session that you would like to run, there's a whiteboard over there with some Post-its. Please go ahead and throw your ideas up over there and just kind of self-organize into Unconferencing. Great. I am now going to bring up Joshua, who is going to talk about our code of conduct, social rules, and introduce our very first speaker. So thank you.
Hello, good morning, Bang Bang Con. Okay, I have a handful of things. Oh, wait, there's a button I can press. Wait, Erdy, you didn't talk about our sponsors. Well, I'll talk about our sponsors. That'll work. Okay, so Erdy alluded to the concept that we have a whole bunch of sponsors who are making this possible. And so let me just quickly run down a handful of these sponsors, which is to say all of them. Button Down is an awesome level sponsor this year. They do email, and I like their UI better than MailChimp's, and I'm not just saying that because they're paying us, and MailChimp used to pay us, and Button Down pays us now. But I actually spent like the last couple of days, I like the input, I like the editor for, also you can, I don't know if you noticed in the email that I sent, you can put LaTeX in it. So that's really something. Accelerated Tech is a little 2-person consultancy, of which I am half. Anyway, if you need somebody to do software or hardware or firmware, or really, if you need a Joshua and my business partner Jamie, then please hire us to work for you. Meyer for Hire. Jim Meyer sponsored, which swag did, the cushions, right? Cushions, all right, so the button cushion, or the butt cushions that are over there, and the keychains, that's right. The butt cushions that you may be sitting on, the keychains that you may have, and if you didn't grab a butt cushion or a keychain, and you decide that these chairs are firmer than you would like, then I encourage you to grab precisely 1 butt cushion, not greater than 1. Anyway, Jim Meyer sponsored those. Magic Button Club. Okay, so we have these buttons over there that look like normal, ordinary button pins, except they are also NFC tags. And that's, I think that's cool. So I think that's kind of exciting. Okay, Baskin Engineering. So the Baskin School of Engineering at UC Santa Cruz here sponsors this. This is the venue that we are at. They are just like letting us set up shop here. And that's fantastic. And in particular, I am extremely excited about having Bang Bang Con in the freaking Redwoods. Yeah, right. So if you see a banana slug around, then wave hello to the banana slug. The banana slug would be the conference sponsor. Okay, so Nicole, who will be speaking in the first block, was our sponsor for coffee. So if you like caffeine as part of your conference, right. I have found that to be an integral part of my morning this morning so far. And finally, Stanton Ventures is sponsoring our famous live captioning. And I think that's a super important part of Bang Bang Con. And actually, that kind of segues into what I really wanted to talk about, which is, well, actually, I also really wanted to talk about this. But what Ernie called me up here to talk about. So I wanted to talk a little bit about our code of conduct. And often there's this code of conduct discussion at the beginning of a conference where somebody is like, do not do the bad thing. And I broadly trust you all to not do the bad thing. It is written in the code of conduct, by the way, that you ought not behave poorly towards each other. But our code of conduct is less about defining what not to do and more about intentionally defining the culture that we want at Bang Bang Con. And indeed, it also specifies that we do not want you to be harassing each other and such things. So yes, the code of conduct is a list of suggestions of ways to act in kind ways towards each other, and has a bunch of suggestions there, and like also enumerates a handful of ways that some are obvious and some are less obvious about how people can be unkind to each other. And so, but I think it's different than, it's not a copy and paste code of conduct anyway. So I wanted to say that it applies not just while we're here in the courtyard, but in conference adjacent spaces. So that means that I expect that you all will be kind to each other when you go out to dinner later, or if you don't go out to dinner later, or if you have lunch later, or whatever it is. I expect that I don't think this is going to be a problem. I really don't. Bang Bang Con attendees are the best. Anyway, so if you have questions, if you have comments about it, all that kind of stuff, how to get in touch with us. Obviously, we have highlighter blue shirts and should be easy enough to find. You can message us on Discord. You can send email to 2024-organizers@!foundation. And on this Code of Conduct webpage, there is an anonymous form. And if you are thinking like, oh, whatever I saw doesn't rise to the level of telling somebody this or that or the other thing, one of the things that we actually want to know is like what smaller things, even that you don't think that we need to take action on, are happening, either good or bad. And we try to compile a report of like, okay, how did we, sort of a postmortem of how did we do, and how could we improve, and what are ways that we can guide people, like what are the non-obvious things that we can guide people towards later. So anyway, I'm rambling on for quite a while, and I have only 2 more things to say. So one, on the Code of Conduct subject, there are 4 social rules that we inherited from Recurse Center. And they're specific things that are easy to accidentally do. And so they're so interesting that we call them out specially. There's this concept of backseat driving, which, again, these are things that like at least I find them non-obvious, and I have to constantly check myself. And so I think it's preferable anyway if you're hearing somebody saying something and you're like, huh, like that's an interesting conversation, and that like one fact in there was not correct. Please join the entire conversation. Do not just like drive by somebody with a like correction and a backseat driving there. This one is, I think a lot more people are thinking about this, like since we started Bang Bang Con 10 years plus ago. But like, it's easy to have subtle isms in how you speak. And so I think about like, I caught myself the other day going like, no, like, look, my mom understands how to use Signal, like, and it is true, but also that gives the impression that my mom is not technical. My mom is actually very technical. So anyway, see if you can avoid that. There's a common phrase anytime you're about to correct somebody subtly and say like, well, actually, just please don't do that. And just like, just please, like, if you cannot, that's better. And the other like cool one is that there's this idea that like sometimes we like to feign surprise when somebody doesn't know something. And actually not knowing something is the coolest part of Bang Bang Con, I think. There's a lot of things today that I know absolutely nothing about, and that people are actually genuinely surprised that I don't know about. And so anyway, if somebody doesn't know something, then fantastic. We are here to, that is the thing that we are here to do. So, okay. Health, sun, we are outside. Please remember to wear sunblock. I believe we have some. Ask an organizer, ask your friends. It is going to be sunny today, it looks like, which is lovely. But also, that means that burnination may happen. Infectious disease. I will be wearing a mask for most of the conference. You may do as you choose. But even though I had COVID a couple of weeks ago and I'm unlikely to get it again, I don't want con crud. And I don't want to give any of you con crud. So I think like masks are just kind of nice. But anyway, you're welcome to do whatever you like. But it is not weird if you wear a mask and if you're like, I can't tell whether that's allergies or not, and you're all feeling all anxious about like, is that allergies? Like, will people look at me funny if I wear a mask? Am I being irresponsible? Just wear it. It's fine. You're good. Okay. Now, the procedural stuff is over. I'm really excited to introduce Dawn Walker. Dawn will be talking to us about making local and accountable tech. And I was reading Dawn's abstract, and she had said, my trick is to act like the future of computing that I want already exists in the world, and I get to hang out there. And she's going to talk about why the future should be more local and how to bring it into the present and how to build tech together. And I think this is going to be a refrain that we're going to hear a bunch over the course of today and tomorrow. And we were talking a bunch about this as a team, and like yesterday and over the weeks leading up to this. So I think this is like a really fantastic way to start off our conference. So Dawn is a researcher and designer interested in how computing intersects with just transitions. She started a tech worker co-op, participated in community-led archiving of environmental and climate data, and schemed about mesh networking, to name a few things, in her attempts to create alternatives to existing ways of building and stewarding technology. Since 2017, she has co-organized Our Networks, a conference about the past, present, and future of building our own network infrastructure, hosted in Toronto and Vancouver. Please welcome Dawn Walker. Got it.
Just arranging everything. Ugh, okay. I think I'm good. Yeah. Hi, everyone. Good morning. Okay, I'm on. So yeah, I'm very excited to be here. And today I'll talk about some previous decentralized and local projects and hopefully manage to share why I think local and accountable forms of computing are interesting, joyful, and fun to create with others. My name is Dawn. As you heard, I'm a designer and researcher. I'm usually based on unceded and ancestral territory of the Hunkaminam and Squamish-speaking peoples in so-called New Westminster, BC. Probably like many of you, I was captivated by computers early on, and they've been a part of a number of formative childhood memories. Though my understanding of what I was doing in those moments has probably changed over time. For example, I thought we were playing Civ 1 in my elementary school computer lab, but have since realized we were actually just trying to get through the copy protection quiz at the beginning without a manual, by building up kind of like a shared knowledge amongst us of what those answers were and many unsuccessful attempts. And though unfortunately, I have only memories. While I was preparing this talk, I thought I'd get one of those like cute, out-of-computer young photos to share with you. And I asked my mom if she had any old pictures of me, but she sent me this instead, which is me holding our pet garter snake. So I'll offer this to you. So yeah, in my bio it said, while I'm interested in technology, it's always been about other things, what possibilities for a better world it could enable. And to think about those, I like to use the framework of just transition. Here you see a portion of a rather elaborate diagram from the Climate Justice Alliance with the words, "Stop the bad, build the new." And under an arrow with another phrase, solutions that are visionary and oppositional. A just transition is aiming to ensure that no one is left behind or pushed behind while building economic and political power. I think most of my projects are a way to ask myself, what could computers call into the present? How do they build alternatives, especially in this moment, AKA my entire adult life, when it feels like everything is already falling apart? To set the stage for the rest of this talk, I wanted to rewind back to 2015. I've just spent 9 hours on a megabus, headed to New York from Toronto, to attend what will be the first of many radical networks. After 2 dizzying days of workshops and talks about DIY networking, mesh, and offline networks, where I meet some people who are also from Toronto that I didn't know before, I leave and take a bus back home, wishing events and projects like that were nearby and local to me. Back where I live, through Civic Tech Toronto, which is a still running, I think also decade-long weekly hack night, I meet others interested in those topics, and we set out as Toronto Mesh, testing antennas, configuring mesh nodes. We started with a Raspberry Pi using CJDNS, and hosting workshops, all the while scheming about a first line-of-sight connection. This is one of the other TO Mesh members, Ben, circa 2016, I think. TO Mesh today is largely dormant and probably didn't achieve our wildest dreams. Fair, they were pretty big. But I organized an event on January 2017 called State of Our Networks. And to some extent, I've sort of been like on this path ever since. With that title, I was drawing inspiration from Bruce LeBouse and G.B. Jones, who called into existence the Toronto queercore punk scene of the 1980s and 90s. I was acting as if there was already multiple overlapping projects in a similar. It wasn't, it was just us. But part of what G.B. Jones and Bruce LeBouse were doing was art project, part necessary for life, and it was covering a culture that didn't yet exist in their zine, JDs, and presenting it as if it was already there. And as I said, after that first event, I've been in some sort of way doing this ever since, in kind of like a Katamari Damacy voyage through networking and that infrastructure. Before I talk about some of the projects, I just want to like mess up what might sound like a tidy narrative. As this was happening, what I was actually supposed to be doing was researching tools, maps, and information systems that aided urban agriculture, and with an eye to questions of participation, but somehow figuring out whether, how, or if more distributed and local networks could fit in became like a side quest that turned into a main quest. It showed up in a project to preserve access to data about climate and the environment when supporting institutions may no longer be able to or desire to. During times of perhaps political instability, remember early 2017, we wound up creating an open source prototype for decentralized storage and verification of archive web pages and data sets, as well as piloted the social apparatuses around it. It also connected me to a group of collaborators and comrades who I eventually started a tech worker co-op with in order to consider the labor that goes into the projects we all work on. This is not an image from our co-op, it's from another one, IMOL Arts and Technology Co-op that I particularly love. Also more on this theme later. It also got into my head during my PhD and eventually led me to trace how one particular value in design, decentralization, was being deployed in a divergent range of topics. Also more on that later. And then finally, we'll see how it crops up in my current role as a service designer for the Environmental Protection Division of my provincial government. Though I have to make a typical disclaimer, these opinions are my own and do not reflect my employer's. So, revisiting our networks. We just wrapped the 6 R networks this summer. Our theme was Does Not Cloud Compute, and we were inspired by practices that transition using local-first software, that adopt folk software tactics, and that are based in repair culture guided by perma-computing principles. We're always trying to balance a few different things. Like first, how do we look to the past without engaging in nostalgia? Second, how do we connect to what people are already doing right now? And then third, how do we think from both of those about a future in which many futures fit? This year in particular, I think really rooted in place, we were curious about experiments in telecommunication arts in the 1970s and 80s in Vancouver and Victoria by artists at 3 media arts centers. Hank Bull out of Western Front and Bill Bartlett from Open Space in particular put on a series of performances with what was an emerging technology at the time, slow scan television. It's a low bandwidth way of transmitting images using radio frequencies that also produces an audible tone. Artists would participate by transmitting and receiving each other's performances at pre-specified times, but all of that coordination had to be done out of band. Speaking with Hank Bull about this interplay of kind of that coordination and that technology, it highlighted, if it wasn't already apparent to us, all the ways that all that is required to develop and share new practices, if it wasn't already on our minds. On the screen is a photo. I went too fast. On a screen is a photo by Sharon Lovett from the Vivo Media Arts Center page of one of those performances. To learn more, we went and visited the archives. We got permission to share some of the material and recordings of the performance on a local network that we hosted at the event. We created the site to do so. We also made a zine about those visits and digital archiving, which lays out some perspective protocols, see what I did there, to do amateur event archiving with open source tools and hosted services, though the same ones that we've been using over the years. That includes the Internet Archive upload feature, wget, Mailman, and Git. I know, bold choice. We also referenced those slow scan performances in our stream. We set up a Raspberry Pi running FFmpeg and Media MTX to create a low bandwidth stream equivalent. It only used 8 shades of black and gray, less than a frame per second, alongside the audio track of the day. Preparing for this led to some real FFmpeg hair pulling moments, and I might now understand filters. I'm going to claim that. In previous editions, we also developed a way to stream over IPFS, a protocol for distributed file sharing and storage using content addressing, at the same time that viewers could select streaming over HTTP. For our 2022 edition, we held a series of online write-a-thons in place of a typical conference, where we co-wrote a wiki representing an artifact from 20 years in the future, in 2047. Our aim was to collectively narrate the steps that it might take to get to there from our present. We hosted our own media wiki, along with a guide on how to speculate together with care. Who knew the future would arrive on a wiki? Certainly not me. What we wound up with was a fabulated conference program full of groups, ideas, and moments that have yet to be, but are suggestive of directions to head. We closed it to editing after the event, took it down, generated a static version that worked locally, and sent that out to registered attendees via USB with an accompanying zine. I've been talking mostly about an event, but it's not the only container to explore new practices around computing through. As mentioned in my bio, another one is that I've been looking at is what formal and durable structures help scaffold practices and allow them to last. Through Toronto Mesh, I met a group of collaborators and comrades over a lot of time and many conversations. We decided to start a tech worker co-op to hopefully earn a living around our various open source schemes. It was a crash course in learning about all of the traditional roles and structures and reporting requirements that are enshrined in law to operate as a firm. We all got to be member owners with an equal percentage. We opted to be a nonprofit. We strove for a flat structure with a largely ceremonial board, pushing as many governance decisions as possible to the day-to-day operational layer. And that day-to-day, I think, looked pretty similar as it could elsewhere. It involved client-based work, some in this space, some with arts organizations, nonprofits, or companies, alongside a mix of our own projects. We started by self-hosting, probably too many things, but also aligning that with existing services to set up a virtual office, and committed to sharing openly. We also got to, maybe this is more like had to, think through those decision points and operational rhythms that help us maintain what it is we wanted to do together. Shout out to that organization, Haifa, which is still going strong. I'm no longer with the co-op, but after that DIY introduction, I've helped others incorporate since. Most recently, I've been a member of CoSocial, small plug, a community service cooperative, also a nonprofit, that is formed to run a Mastodon instance in so-called Canada. There's a lot of direct inspiration that I personally drew from in being a part of this, including democratically run formal and informal co-ops of all types that have been formed around tech infrastructure. Social.coop is another Fediverse one. Meet.coop for video, it's Big Blue Button based. And finally, May 1st, Movement Technology for like the nitty gritty of a range of shared infrastructure, particularly mail servers, can't believe they do that, who have operated as a co-op for almost 20 years. To help myself make sense of what I've been doing, I wanted to talk through kind of the set of slowly accumulating ideas that have guided me. Perhaps most obvious for the language of networks, I spent a lot of time thinking about decentralization and distribution. Both are terms with long histories, which, as you also have probably noticed, are having recent waves of interest as part of calls to take back control of our data, the web, the internet. There's sort of a rough story there that goes something like, the internet was originally designed to be decentralized, and while that ideal persists on infrastructure no single authority can own, increasingly the things we do on it and parts of how it operates are controlled by a handful of companies. This story has been told by various groups, from that Bitcoin white paper way back in 2008, 9, social movement, early social networks, including Diaspora, remember 2010? I barely do. Or movements and design patterns like IndieWeb. I think its first camp was like also around that time. To more recently, in 2015, the decentralized web community with their collectively authored set of principles that focus on human agency, and an event series originally convened by the Internet Archive. There was just a recent DWeb camp nearby here in August, and I kind of suspect some people in the audience attended. And also through something like Web3, which was coined around the same time and has an accompanying foundation. However, while being popular, the term decentralization I find pretty slippery. A decentralized network could look like a lot of different things. It could be like that famous image of a majority of Bitcoin miners all sitting together on a stage. It could also look like a geographically distributed group who are running nodes on some sort of network that they've built together, but they wind up all being on Amazon AWS. Or it could be like a peer-to-peer social media where your identity is tied to your individual device, and you keep a copy of all of that on your local hard drive. And if you lose that, it's going to be a little bit hard to get back on. I won't trace all the twists of this recent wave of interest or unpack sort of these ebbs and flows, but if you want to have this conversation, come find me after. I'm here all weekend. But to make a long story short, decentralization is inflected by context. The decentralization of the DWeb community and their collectively authored principles is not the same as the fever dream of decentralization to win the future that was pushed heavily by venture capitalist firms like Andreessen Horowitz, maybe most popularly starting in 2021, 2022. Thankfully, well, maybe not thankfully, but we've seen some market corrections, which has sort of lessened that fever dream. And there's been a pivot to the next big thing, AI, which I will not talk about. For me, the recently ascendant visions of decentralization feel a bit like a dead end for some of those more transitional and interesting and emancipatory versions. And so I'm cautious about how to use the term. I feel like at times it gets to be more unhelpful than clarifying. And what I've seen often is that, like, when you use it, a broadly and a popular but broadly imprecise idea gets communicated, and it doesn't actually help align individual interests, and it has a flexibility that both is an opportunity but a challenge. And here I'm contextualizing a meme from Sarah Friend. So that's roughly where I wound up at the end of my PhD. Decentralization doesn't capture everything I might want. I have some reservations. So why not use the word local instead? Okay, I didn't exactly bandwagon jump then. This is just me trying to do a bridge and a talk. Others, far sharper than me, have taken a different approach to thinking about the same issues decentralistas name. The things that we do on our computers are controlled by a handful of companies. They don't give us a say over what they do with it or how we can use their services. Ink and Switch, an independent research lab, published an article in 2019 called Local First Software. It's excellent. If you haven't checked it out, maybe do. They also have a reference implementation that's quite popular, built that kind of like models these ideals. They lay out a set of ideals that would enable software to support both real-time collaboration, which to me right now is probably one of the main things I'm doing with other people online, and ownership for users. As opposed to putting all your data on a server somewhere and then being stuck when that service shuts down, starts platforming fascists, stops working on your devices, or like somehow experiences catastrophic data loss. I won't go through all of these in depth, but those 7 ideals cover the idea that we shouldn't have to wait for our data. It should follow us across our devices. It shouldn't matter if we're offline or not. And if we do go offline, it should eventually sync and gracefully resolve those conflicts once we come back. That access should persist for a very long time in a secure and private way we have a say in. They also reference data structures like CRDTs, conflict-free replicated data types, that they see as foundational. When they talk about local, it's often explicitly about data, storage, and networks. For me, the term, though, also broadly explains a thing I want my projects to do. When I'm referencing something like decentralization, I mean something like, I want the site of control to be closer to me, or it could be me, or me and my friends. I don't want that responsibility, or an organization I run. That nearness, that proximity to me and my goals is supported by thinking local to me because it implies a location, a specific place in a network. It also helps that local first, I think, works against the grain of the current web, which assumes a universal type of user that's always connected and steadily powered, which has led to experiences that already and always continue to leave people behind. Brooklyn Zelenka, who spoke at our networks about local first, also gave a status update on those 7 ideals. She mentions that some of them have a lot of progress made, some are actively where work is happening, and a couple have open problems for the next era of work. She also set expectations. I'm stealing a slide from her deck. It's amazing. Where local first is not even at the early adoption phase. It's got to get over a first chasm before it moves into from a group of innovators into early adopters. Mauve Sineweaver, in their talk on holistic local first software on the peer-to-peer web at Causal Islands, also points out that with local first you get to kind of revisit certain questions of complexity and figure out where you want them to show up. Certain types of complexity maybe could even be avoided in a traditional flow, say for instance, bespoke deployments, and the need for like a lot of DevOps knowledge. All of this leaves me feeling hopeful and in a pragmatic way that I can work with, full of ideas for future projects. Next, I just want to pull quickly on a thread of being in a place. And so I reread this paper from Lucy Suchman that always sticks with me, Located Accountabilities in Technology Production. Suchman is a design practitioner and academic who worked at Xerox PARC for over 20 years. In 2002, she was writing about what an alternative practice of technology production and use could look like. Key to her was focusing on all that work that's required to actually stabilize a new technology, and that an awareness of one's location within an extended network of relations. With that awareness, she says, there comes a sort of recognition that developers don't have all the control, and that the question at each turn should become, how do we proceed in a responsible way? In the paper, Suchman also lays out how a lack of awareness results in a design from nowhere. And to paraphrase her, what that means is people problematize the world in such a way that their very specific skill is indispensable to it, and then they discuss an obligation they have to intervene. Ultimately, to her, these ways of being nowhere, while claiming to see comprehensively, need to be replaced with a view from somewhere, a located accountability. And I think that's something like what a local orientation to software and computing can provide. A way to become answerable for what we learn how to see and build, even as we continue to do it for ourselves and with others. In terms of what that looks like for a resulting system, there's something about that which echoes my own experience. There's these kind of like artful integrations, in Suchman's words, hybrid systems composed of a lot of different devices where new interactions and more powerful integrations across and between devices and their settings of use are important. So, kind of getting closer to the end, taking a step back, I want to recap some of the lessons I've learned. Looking to already existing practices elsewhere. Looking what things were like in the not too distant past, looking at opportunities to make something new. Those aren't the only things I've adapted. I think the main one is that there's something powerful about acting like the thing you want to see in the world already exists. I also truly think one of my real skills is that I try to find a way to use a thing outside of maybe the context it wasn't intended to be used in. So some more specific bits that have helped me do that. First, doing it with others. This is a term from further field. It could mean in a lot of ways, by directly collaborating, by seeing yourself as part of a common cause, by engaging in forms of solidarity, like selecting the tools or services you use, finding those neighbors that you have more in common with. The image on screen is from Further Field's distributed campaign for emancipatory network art that they instigated back in 2006. It also leads me to the next one. Cite prior art and make those explicit connections, like this image, which is from the Lurk crew, who runs a lot of different shared infrastructure and collectively documents it, including post.lurk.org, which is a Mastodon instance. Next, embedding tech in larger experience, especially a social one, aka LARP it or it didn't happen. I didn't even get to a part of our networks where one year we had Michael Coney join us to help create an alternative reality experience led through a series of workshops to kind of like prospectively think about some networking themes in an alternate reality. I'm using an meme, I think, of the internet here, lightning bolt. Next, by gluing existing things together. If it's done in an interesting way, I think it can be as relevant as building something brand new. I think, as you've seen, most of the software and tools I've mentioned are pretty straightforward. But I think used in the right spot or stitched together with others, they sort of get at something interesting. I've meandered. I'm about to reach the end. I wanted to close out by expanding on the kicker from my abstract. The future of computing should be more local, in ways that are located and therefore accountable. As doing something somewhere as opposed to a view from nowhere. And hopefully soon, in a way that relies on local first software. I'm ready to be an enthusiastic early adopter in as many uses as possible. It can also be brought to the present by acting like the thing you want to see in the world already exists, and by finding ways to do difficult things together and to be changed by that experience. And then finally, about that done together bit. There's about 1 million ways, all the unstructured ways we're already doing things together. But I've tried some of those more durable ones, forming a sort of collective, accidentally producing an event for many years, starting a formal legal entity, preferably a co-op or social enterprise, or being a part of a movement, something like, say, the Tech Worker Coalition. And sometimes my favorite move is volunteering to help out at someone else's thing. I'll stop there. Thank you. Do I leave them? Oh, okay.
Thank you, Dawn. I brought a coffee up here, and I have no idea what I was going to do with it. Thank you, Dawn. Okay, so we are having a break for 10 minutes, which means that we return at 11:30, which gives you time to apply additional caffeine, apply additional sunscreen, apply additional pastries. If you are presenting in the first block, can you come find me sometime in the next 10 minutes so we can do an AV check? Okay, you're free. Thank you.
Thanks.
Fantastic. found me. Okay.
Yeah,
Let's see if that maybe check.
Go buy some more.
Do we know whose watch this is? There's a watch here.
Which buys, not like the far this guy.
Hello. Okay, I think we're going to start again momentarily. So, return to a seat or a standing in the shade. Or, I know we said don't move the furniture, but maybe move the little chairs into the shade if you like. Maybe that's okay.
I couldn't understand. Also.
Hello, hello. Please come back. Come back, Bang Bang Con. Come back. Return to your seats, Bang Bang Con. Or to something approximating a seat, which is also fine. Ooh. Return, Bang Bang Con, or at least stop talking. That means you. Erdy is just going to stand there and hold an umbrella for the rest of the conference. Okay. Well, if you return, then fantastic, and if you do not return, then you are welcome to stand wherever or sit wherever is shady. Also, speaking of shady and sun and such things, when I said earlier that I recommend applying sunscreen, I definitely recommend applying sunscreen, and I recommend it so much that we have some at the registration table, and I think also many other people may have sunscreen around, and so either ask your neighbors, or if you do not have some, or feel free to have ours, and I think we're going to get more than because it is sunnier than we expected. Anyway, so coming back to Bang Bang Con stuff. I have this like vague meditation on Bang Bang Con as separate and the same as the rest of the world. I grew up, how do I make this stop doing that? There we go, okay. So I grew up in a Jewish household, and there's this concept on Friday night or Friday and Saturday of the day of rest, Shabbat, and it's your break from worldly obligations is the idea. It is distinct from the everything else, and I'll either assume about your experience or not. Like if you grew up Jewish, then you may have an idea. If your friends grew up Jewish, if you knew somebody of this, then you maybe have the idea of walking into an aroma of chicken soup in a house that is cooking. And the differentiation of like warm challah bread on Friday night and conceptually lighting candles. And I should note, by the way, that like this is something that even if you've never done it, like for many people who grew up Jewish, even if you've never done it before, you did it like once or twice, it is a memory that you have even if it never actually happened to you. And so, but this concept is called the Shabbat spice. It is a secret ingredient in the food that is prepared that makes the food taste better. And so non-observant Jews sometimes smell the Shabbat spice. And so I think about this as a differentiator of Bang Bang Con as well. I think about like an alternative world. If you think of that as the alternative world for a day, I think about the other, Bang Bang Con is another alternative world where during the week, during the rest of our lives, we be productive and do computing about things that change the world, this, that, the other thing, write programs to make people money. And at Bang Bang Con, I like this difference that instead we have this opportunity to relish in kind of the joy and like the rest of computing and have a time to do it together. So I think about Bang Bang Con is different and distinct from the rest of our days. And I just wanted to give you that invitation to, even if you have work to do later, to feel okay about holding the joy of Bang Bang Con now and let the Bang Bang Con spice show up a little bit. So I wanted to use that to start as an introduction also for our first speaker, Nicole, whose last name is unpronounceable, and she has told me that it is okay that her last name is, I asked how to pronounce it, and she said it is unpronounceable. So I'm not just making that up. And she's going to tell us about programming with only exceptions in her language, Hurl. Nicole is a principal software engineer at Remesh, where she focuses on software architecture, performance, scalability, and security. Outside of work, she plays with her kids, spends too much time on computers, hangs out at the Recurse Center, and drinks tons of decaf coffee. Welcome, Nicole, whose last name is unpronounceable.
Thank you. So part of why I told him not to worry about pronouncing my name is it's very handy if there's ever a deep fake video of someone in my family saying that they want money. If they know how to pronounce my last name, I know it's someone who actually knows me and who is related to me. So yeah, it's so wonderful to be here, to see so many people. It feels like a lot of old and new friends. So I'm going to tell you a story today that starts in January 2023 at Recurse Center. After my batch finished, I was talking with my friend Mary McGrath, if you want to know who ultimately to blame for what happened afterwards. They did tell me I could share their full name. So thank you, Mary. And we were talking about one of the curious things that you see in Python sometimes, which is the use of exceptions in ways that you would not expect in other languages like Java or C++, where they're just for things that you don't expect to happen. And to show what I'm talking about specifically in Python, I feel like we should just look at an example. So something that you sometimes will want to do is check if a string is an integer or not. And in Python, we would want a function signature that asks, is this an integer? Takes in a string, returns a Boolean. So if you give it the string 1, that should say true. If you give it just a letter like A, it should say false. And if you give it 1A, that should also say false. What do we have inside of it? We have exceptions. We just try it. If it fails, it's not an integer, but if it succeeds, it is. And this is kind of delightful and horrifying at the same time. So naturally, we ask the question, how far could you take exceptions? And we were just musing about, like, could you have a whole programming language where you replace constructs with it? What could you get rid of? And as the Beatles taught us, all you need is exceptions. And so I took it way too far, like I do with very, very many things, and I made the programming language Hurl. I did upload my slides with a captioner because so many people mishear me as the programming language Perl. So if you see the programming language Perl with a P, that's Hurl. If you see Hurl with an H, it's probably this one. And like all super serious languages, it has a documentation site. You can find it at hurl.wtf. It has a standard library to do some of the things that you're going to need to do for any practical language, string manipulation, things like that. Has a few licenses, including a custom license, and we offer commercial licensing, see me after. And it has a code formatter, so you can maintain consistent style when you're using this in production environments. So how does Hurl work? I'm going to give you a little whirlwind. You can, of course, find more on the repository or on the docs site. You have three main features that make this language work. You have variables, you have functions, which are all anonymous, and you have exceptions, which you can throw and catch. As the Beatles told us, this is all we need. So in Hurl, your variables are dynamically typed. You can reassign to them. So you can create a string, then use the same variable name for a number. It doesn't matter. It's all good. It's dynamically typed, maybe as a principal choice, maybe just because that was a lot easier for me to implement. You also have functions, and all functions, like I said, are anonymous, but because we have variables, you can bind them to a name. And because I also was lazy and I did dynamic name resolution instead of doing it at parse time, you can recurse with that. This is regrettable if anyone actually wants to make a very, very, very deep patch to this to remove the ability to do anonymous functions. I would love that because I wanted you to have to pass the function into itself to recurse. But whatever. So you can write a function like this that will just recurse until you hit the stack depth and stack overflow, and that will tell you what the depth of your stack is. Very useful. We need to know this. And then you can do the normal things. You have arithmetic, so you can get stuff done for your production calculations, string concatenation. You can also include other files. So if you have mischief in this one, you can include your mischief. But you can include whatever you want, so you can pass in any expression as long as it forms a string. That's what we're going to look for on the disk. So you can construct dynamic includes at runtime. And I had kind of been trying to avoid it. I guess I do have to talk about it, but yeah, exceptions. There are two forms of exceptions. You can hurl an exception, which is what you expect, kind of the usual. You throw it, it destroys stack frames as it unwinds the stack as you go. And then you have tossing an expression, which is totally extra, but it's there because it was really a cute idea. And what it lets you do is it walks the stack, keeping all the stack frames. And then if you use the return keyword, which we all know and love, to do what it actually sounds like it's doing, which is going back to where you came from, you return, then the tossed exception will go back to where you tossed it from, and you'll keep executing from there. And there are three ways you can handle it. You can catch a literal value like 1 or true. You can catch as a local identifier to make a new local variable, or catch into an existing variable. So now we have some examples. This is a Python program many of you are probably familiar with, print hello world. It is also syntactically valid Hurl. For something with more interesting logic, we can greet attendees. Imagine that we form this variable some other way. It's not just hard-coded. Then we can hurl whether or not you attended Bang Bang Con and catch true or false and greet you appropriately. You can count to 10. So what you would do here is you have a recursive function, and each iteration you pass it in. Eventually you catch the literal for your base case. That's how you stop recursion. And you would print something like ready or not, here I come. I've been playing hide and go seek with my kids. Now we'll look at a working example. This is our standard in Python for factorial. It has a base case of n equals 0, and then you have your recursive step, and then you'll print it out. So we can actually mechanically translate this into Hurl. It all converts pretty easily. First, we define our function. Then we define our base case, which, since we don't have returning out of functions the normal way, we have to hurl out of the function and then catch it as the return result. And then when we recurse, we will we have a catch false, and then inside that we will create our variable, recurse to calculate the next step, hurl that out, and eventually print it out. So you can dive deep into that, as I know all of you will, because this is a lovely language. But the point is that we can translate any Python program into this, and it generalizes over any computation you want to do. So we have standard library. In standard library, I actually implemented if else because it was kind of annoying to not have it, but you can implement it in terms of just exceptions and play more like loops. Then you also have the custom licenses like I talked about. So you have the commercial one that's pay me bags of money, which would be hilarious, and I hope no one does because you really should not actually do this in production. You have the AGPL because, yeah, let's keep software free. And you also have the gay agenda license, which I think I'm going to give Mindy a partial blame on this one. But you have to say be gay, do crime at least once while using the software, or you lose your license. And if you ever do something that impinges on LGBTQ rights, you irrevocably lose your license. Hurl does have some limitations because no language is perfect. The call stack size obviously is limited by your operating system, and since I did a tree walk interpreter, I don't have a way around that. There are bugs in the interpreter, especially with toss, which is embarrassing because that was kind of cute and extra, and it has a lot of bugs. And it's really painful to debug and profile, but none of it matters because Hurl is a useful language. And you probably don't agree with me right now, but the point is that it's about joy and learning and silliness and connection. And like, I don't know that I would be talking to all of you right now if I hadn't made this silly, ridiculous language, and I get to meet so many cool people. So now we're just going to take a hard pivot and talk about my workshop. I also do woodworking. Some of you have asked me about my keyboard setup, and I made it out there. This is my workshop when I had that's a coat rack I just finished making for my kids. In the picture, you can see my workbench, which I made myself. I've also made sawhorses that I use, and I've made a lot of sleds and jigs, some of which also were useful in making that coat rack. But I can't make my chisels, I can't make my saws, the vacuums, power tools I use, things like that. As programmers, we're in a really special position because we can make all of our own tools. And so we build everything, programming languages, OSs, debuggers, editors, browsers, even our conferences. And so I learned a lot from building Hurl. Like parser errors make a lot more sense to me now. I have a different way of thinking about code and appreciate normal control flow a lot more. And appreciate a lot of my friends who are along for this really weird, wild ride. And silliness is freeing because mistakes can be an aesthetic. So go forth, be swift, make more silly things, especially so I can make more sentences out of just programming language names. And thank you so much. If you haven't hurled yet, you can find me on my blog or Mastodon or my newsletter.
Thank you, Nicole. That's enjoyable. That's fun. I agree. We make things because we want to. Okay, so next up we have Amadei Daboville, and I will preface my introduction to say that I am not a ML is everything believer. I'm not an ML true believer. I think the techniques work fine. They work on large scale for some things, but more interesting to me actually is going small for ML techniques. And so Amadei Daboville is going to talk to us about running a tiny chess neural network by hand. What is the smallest possible chess neural network that we can run? Amadei is a full stack software engineer from Montreal, now moving to Amsterdam. Come up. There you go. They like growing culinary mushrooms, playing chess, and techno music. Please welcome Amadei Daboville.
All right, hello. Great, thank you. All right, hi everyone, my name's Amadei. I go by they, and this is Let's Run a Chess Neural Network by Hand. So why would we want to do that? And my reason is I got into chess during Queen's Gambit like everyone else, and I heard this story of a guy who wasn't a chess person, but he got the opportunity to play the world chess champion, Magnus Carlsen, and he didn't know that much chess, but he was supposed to ultra learn as fast as he could, and then play and then see how it would go. But then he decided to take a different approach, and he decided that instead he was going to encode during the game. He would write down the board as a list of numbers, and then he would run a neural network, and then the neural network would tell him if his move was good or bad. And I really liked that idea. I thought that didn't really work for him. He didn't end up using that, and he still lost. But I just thought that if you did that, it's kind of a fun idea. I don't think it can work, so I looked into it. And just in general, computers are so strong. We have supercomputers on our watches. Maybe these things that are so much better than us, maybe if we made them weaker, maybe we could meet somewhere interesting, I guess. And the answer for whether it will work or not is probably not. The way that chess engines work is that they search through this tree of every single possibility, and they search millions and millions of positions. And there's no way to do that humanly. We've heard neural networks are everywhere and everything, and we've probably heard of AlphaZero, which briefly beat the world's best engine, Stockfish, for a little bit. But then Stockfish took the crown back and just went right back to searching that tree millions of times per second. And Stockfish did add a tiny, tiny neural network in 2020, and that helped a lot, and we're going to actually look into running that one. But even this idea that you could take the board and turn it into a list of numbers and just stare at the board once and then get the answer doesn't work, because even AlphaZero and its successor project, Leela, they don't stare at the board once. They still search something like much less, but maybe 50,000 positions per second. And until recently, we didn't even have a neural network that could look at the board once and tell you what the best move to make was. Up until like earlier this year, these people in the middle published this paper saying that they had finally done that you don't need to search, and they did make this model, and if you squint, it's grandmaster level. But they didn't compare themselves to Leela, which is the successor to AlphaZero, which already said they had already done that, and they made this graph, and on the bottom it shows that this BT3 one is the same strength. The y-axis is like relative strength, and it has much fewer parameters. And so right up until maybe last year, we didn't have this, and now we have one, but this has 100 million parameters, and then the top graph shows that it takes 5 billion math operations to do. So we're never going to be able to scale that down. Even if we find a bunch of tricks, we cut that down by 1,000, we're never going to do that. But that's good to know, like, you know, what the ceiling is. But like, what if we still wanted to do it? What if we just, instead of going from the top, maybe we can just see like what's the best we can do with something we can do. So we'll never be grandmasters, but you know, how far could you go? And so I decided I would kind of set some constraints, like how big would we make this? And I saw that someone claimed to memorize 100,000 digits of pi, and so I turned that into like a bytes number. And just to give an idea, in the end, the network, it fits on like these 2 pieces of paper. So you could maybe memorize it, but something around this scale. So I said that I wasn't going to memorize them. I'll put them on some paper. And assume that the game is really long, and so you have time to maybe take half an hour or an hour to just stop and do some math. Also, to make this a little easier, instead of playing with the network itself, we're going to have a human still kind of in the driver's seat, and they will choose some moves, and maybe they pick 2 moves, and we have the network kind of score them, and we pick that one better. But that way, the human still is in the driver's seat and is not, we're not having to depend entirely on the network. So I won't go into this, but just as a recap, neural networks have these matrix multiplications, and then they also have these activation functions that are supposed to be like neurons firing, but it turns out they don't have to be like that. There's one that's called ReLU, and it's like this. And the one we're going to use is clamp ReLU, and instead of that, it's like this. And that's it. And it turns out that makes things really easy. And if you had to do something by hand, I would use this NNUE architecture, which stands for Efficiently Updatable Neural Network, but it's spelled backwards. And it has this killer feature that you can use it as you're going down this tree. You can evaluate it, and then you can undo a move and go back to your previous state. And so you can use this in the searching loop for your engine. It also packs a ton of really cool tricks in a tiny package. There's a lot of sparsity. It reuses weights in ways that shouldn't be possible according to the rules of chess, but it still works. Everything's integers, and it uses SIMD, which everything but the last one is also good if you were going to try and do it by hand. And when they added it when Stockfish added it, they got these 80 points of rating, which translates to like 60%, winning 60% of the time, which for these top competitions, that's a lot. It's like the Olympics, every percent matters. So this was a big jump. I won't go into what makes it efficiently updatable, but here is kind of what it looks like. And if you're familiar with neural networks, this is actually really pretty small. And I thought I could actually even run this by hand. And it turns out because of these clamps in the right columns that are these activations, all the negative numbers become 0. And a lot of values, like 80% of the values in the later stages are all zeros. So I thought you could almost do this by hand, but then I did some napkin math and I realized it would take several hours. So I looked into ways to maybe make this a little bit smaller. You could try and train a smaller version you could quantize it. You could train a smaller version by using this one as a teacher and this one's a student. But it turns out you can use this NNUE features, which is this sparse board representation, and then this idea to combine. You run this layer twice, once from the point of view of the black player and once from the point of view of the white player, and then you combine both perspectives. And this turns out combined with like a much smaller way to represent the chessboard, and you only have one layer. This is just one output layer. This turns out to work fine, and there are people hobbyists who write their own chess engines, and they spend years crafting the way that their engine evaluates a position. So they'll say, if the knights are in the middle, that's good, and the king needs breathing room, and they'll tweak that. And then they'll implement something as small as this that will run by hand even, and this will crush their handwritten evaluation that they've spent years on. And so this is so small, you can ask, like, does this actually do anything? Like, even though people who use them in their own engines, like their engines are still doing millions of positions. So to test this, I used Maya, which is another AI that's trained this time to play more like a human. So in the same way that ChatGPT is trained to predict the next word, this one's trained to predict the next move in a sequence, and you can give it different strengths to play at. And I would have one Maya play on one side, and on the other one, I would have another one generate 2 moves and play the one that this thing preferred. And I tried a few different sizes of this. And at the smallest one, this first row, you can see that if you're a weaker player, you can think of these 3 ratings as like kind of beginner, intermediate, and less intermediate. And if you're doing this and you were actually doing this, maybe you might win against your friend like 54% of it. You're winning like 4% more than you normally would. So, and then with the larger ones, that really translates into like that translates into points, and with the larger ones, you get even like up to these 50 little points. So these are very small improvements, but I think that shows that like the number is positive, and like this could work if you wanted to do it. And so here I have a video of what it looks like. The first step is there's a vector associated with every single feature. There's a vector associated with every single piece on the board and where it is. And then all of them get added together. Is it playing? Am I moving? Yeah, OK. I have to do this fast because it's really slow and really boring to do. I don't actually recommend this. It's so boring. It took like 2 hours. But there's a vector with every piece, and they all get added together. And then we can reuse that the next turn to do this incrementally, where if we want to move a piece from one place to another, we can subtract the vector associated with its old position and add the one for its new position. And that's what I'm doing here, is I'm doing all these additions. And it turns out I'm also really bad at addition. And it took a long time, even though I thought this would be pretty quick. And then the last bit is, afterwards you clamp that output, so all the negative values go to 0. That's pretty quick. And then you have to multiply these. You're just kind of combining them together with different weights. But also, all the negative values went to 0, and everything that was too big went to 127. So I decided to, in my output here, you can't see, but I had a lot of 127. So I decided to just kind of treat those first and to say maybe like 91 is 3/4 of a 127 or something. And instead of doing any multiplications, I would like add the factors, like 5 times 127 plus 2 times 127 is just 5 plus 2. And then here I'm doing you also have to do, like, there's positive ones and negative ones. And so I didn't want to do plus minus, plus minus. I just did all the positive ones on one side, and then all the negative ones, I added those together. And I have to speed this up way, way, way more, and I'm almost done. And at the end, you add these results, and you're supposed to scale this by dividing by something like, by a number to get an actual like score. But I didn't want to do the division either. And since we're doing these kind of relative numbers, we don't actually need to do that. So that's it. That's how I got this. That's running it by hand. I don't actually recommend it, but it's fun to know that you kind of could do this. And I had fun doing this in the computer. So thank you.
Thank you, Amade. Okay, so Amade has given us a concept of taking a particularly complicated computer and making it dramatically less complicated in human scale. The next talk is the opposite. So Jess Wolf will be coming to tell us how to take an astrolabe which was a mechanical apparatus. And rather than building it as a mechanical apparatus, they will tell us how to build it using only digital design and computer-controlled fabrication methods. So I think that is a fun contrast. Anyway, Jess Wolf is a software developer and payments engineer in Portland, Oregon, whose code has almost certainly handled some of your money at some point. They spend their free time misusing technology, doing space math for astrologers, and helping their 6-year-old invent new integer sequences. Please welcome Jess Wolf.
Oh my goodness. Okay. Okay. All right. I'm Jess. You've seen me before. There is sort of a theme to what I do, is that computers and the real world kind of don't quite work together. There's friction there, and that friction is interesting to me. And digital stuff has killed everything. We had all this technology before. It's all gone. It's been replaced with this new generation. Is that good? So I was starting to think about that. I was thinking about what was high-tech before. And the highest high-tech was the astrolabe. For 1,000 years, this was like state-of-the-art. The medieval smartphone is like someone else's talk. It's a lot like the slide rule. It's really a combination of two ancient technologies. The dioptra is a way to measure altitudes. It's kind of like a sextant. And the planisphere, we still use them. They're star maps. And it could do hundreds of other things. It was invented in ancient Greece, or the math was. They were actually made probably in Egypt. Helped touch off the Islamic Golden Age. The knowledge was transmitted back to Europe in time for the Age of Exploration and was still state-of-the-art for hundreds of years until clocks and telescopes sort of killed them in the 1600s. That knowledge has not been lost, but it is sort of rotting. There are websites, most of them are not great. The books are out of print. This guy, James Morrison, spent the 1980s and 1990s figuring out how to do astrolabe stuff with computers of that era. He wrote a textbook about it, and then he died and the book went out of print. An astrolabe is made of parts. Each part is like a standalone thing, and I was like, oh, that actually makes it approachable. I could make them one at a time and see how far I get. So the heart of it is this sort of glorified spherical graph paper, which represents your local sky. So the dot in the middle here, is straight up, and the axis here is like the axis of the Earth. So the stars are turning around you. And you need a different one for where you are on Earth, how far north or south you are. Around that, when I started thinking about this, I had this PCB ruler from Adafruit. Probably some people here make PCB art. I know that's true. you can make other things with it, with that technology, and it's high precision. And I was like, I want to learn how to do that. So to make PCB stuff, you need to use a program like KeyCAD. KeyCAD is hellaciously complicated. And it has an API that I could never get to work, so I couldn't figure out how to do anything programmatically in it. But I discovered that the save file formats are plain text, and you can just edit them. So you can be like, I want to draw a line segment from here to here. I want to write a number here. I want to cut a circle, an arc. It's just numbers, right? So I wrote some Ruby code. I spent a lot of time on Wikipedia learning spherical trigonometry, which was kind of a pain, but everything I do for fun requires trigonometry, so I was like halfway there. So it's not that much code to sort of walk around the circles and project it with spherical trigonometry, and then save it and upload it to someone who can print it. And then you have a physical object that's like really beautiful. And once I had that, I was like, oh crap, I have to do the rest of this project. So the next part, oh, actually, one more thing. So it's code, so you can make variations. So here's for the different bang bang locations, just slightly different view of the sky. Okay, so the next part. So for most of history, transparency was difficult. So to make things that approximated a transparent medium, they would just like cut big holes and stuff. These are star maps. It's not very well suited for PCBs because printed circuit boards are mostly solid. Like you can't cut a lot of holes and it still come out of the machine correctly. So I didn't know what to do. And the other thing is you can't just reuse an old design because the stars drift slightly, about 1 degree every 72 years. So these are from different centuries. And you can tell this star here is Antares, which is a bright red star usually near the horizon. It's this point, this dragon's tongue, and this point. And they've sort of artistically designed the thing around its different positions, and you can sort of see that over the course of 800 years it's moved. And these 3 stars, that's like, this one's in the Big Dipper, this is the same 3 here, and they're like a very different configuration 800 years later. Okay, so I was like, how am I gonna do this? And I didn't know. So I just sat around thinking about it for like 3 years. And I was like, okay, no way, I can do this. I can get the coordinates. I found this Python library that can give you coordinates of stars. So I wrote this thing, just give me the where does a star look like it is from our point of view, and then more trigonometry, just sort of like lay it out, and it's like, okay, now I have this computer-generated stuff that has the points in the right places, but the art stuff is still hard, and I was like doodling, trying to figure out what am I going to do, how am I going to make this, and it's like a creative project, which is way harder than just pure math. And eventually what I came up with is just write thousands of lines of hand-tuned drawing commands. This took like 2 months. If you've ever done turtle graphics or logo, it's like you move in the little arrow around, turn left, turn right, go this far. I just kept doing that until I had drawn the damn thing. And then it's like, okay, now I have this image, what do you do? And I was like, well, you can cut intricate things if you have a laser cutter. So I found this company, SendCutSend, which is great for cutting things out, but they can't do engraving. So you get the shape, but there's no text on it. I eventually found that someone else has a more expensive process called Pinocchio, where they can take the SVG and cut and engrave in one step. And then they sent me these. I was like, okay. And then I just sort of ran with that technology. To make the body of the thing, I just made several. This is me printing out PDFs of the different layers and like holding up to light to say, do these still line up? And they do, and I just screw them together and I have a thing. And then the back, I don't have time to get into it, but this is sort of a standard like Western style astrolabe where all the different apps for doing trigonometry and doing calendar and stuff are all on this side. The Arabic versions had much more variation. Okay, now there's just the only things left are the pointers. I did that in like actual 3D printing. This is OpenSCAD. Its language is like, I want to put a cube here, and then I want to cut a hole in it. And so you're doing a lot of geometry stuff, and it's unions and differences and addition and subtraction. And so it's not that bad, and you can watch, you can have the thing on the screen and just sort of move them around until it looks right. And then you just send it to Shapeways, except they went out of business, so you can't do that. But there's this other service called CraftCloud, and they can do metal the way it works is they 3D print wax, and then they pour molten metals into the wax, so that you can do lost wax casting, but it's all done by computer. And the only downside is you have to get it done overseas. But I went with the cheap ones, and it was fine. And you put it all together, and it looks like it's a real thing. And so, like, to show that this is actually still useful, I'm going to do a real quick demo. It's a simulation. You need direct sunlight to tell the time, and I'm in a shadow right here. But we're going to do it. So first off, you need to measure how high the sun is. It's about 60 degrees up in the air right now. And if you want to line up the two holes in the alidade is the Latin word for it. So the sun comes in the one hole and casts light on the smaller hole. Because if you're measuring like a regular star, you would look through it, but don't do that with the sun. It'll hurt your eyes. Okay, so it's about 60 degrees. You can see the shadows. They're casting about a 60-degree triangle. And then you also need to know where the sun is on the zodiac, on the ecliptic. And so you have a calendar scale. It's August 24th. That's about 2 degrees in Virgo. You find that, you flip it over. Hang on. I should be holding my thing up. You flip it over. You look on this side. And it's like, okay, 2 degrees Virgo. These ticks are actually every other degree because it's tiny. So that's about here. And then you line that up. So, okay, so 2 degrees Virgo is at the 60-degree line. Right there. And then you just put the clock hand, it's called a rule, from there to the outer scale, which has the times on a clock, 10, 10:30, 10:45, a little more than 10:55. Okay, but that's sundial time. That's ancient time. So you need to convert modern offsets. So it's about 1 hour off for daylight savings time. We're about 2 degrees west of the time zone's meridian, so you add 8 minutes for that. And then because it's August and we have modern timekeeping has this analemma thing, you have to add 2 more minutes, and it was about 2:05 when it was perfectly 60. 12:05, it was perfectly 60. And so I'm about out of time. But thank you all so much.
Okay, I'm vaguely offended as a KeyCAD user, as a professional electrical engineer, but also I like to say that KeyCAD has all the usability of Eagle from when I first started doing PCB design, but at a price that fits. It's open source software. Anyway, all joking aside, I do love KeyCAD. Anyway, so yes, the good news is that it is lunchtime. The bad news is that we accidentally scheduled lunch to arrive at 1 o'clock, not at noon. But lunch goes until 1:55. So you may have coffee without anything to soak it up. But otherwise, please mingle and do things and bang bang con. What? Oh, the water has been refilled. I've been informed the water has been refilled. So yes, and lunch will be arriving during lunch, and I will announce when lunch arrives during lunch, or somebody will announce. Okay, have a good break.
Hello? Captioner, can you hear me? Yeah? Okay, cool. Mirabai, you're awesome, by the way.
Very interesting.
All right, everyone. We believe our technical problems are solved. So if you want to go ahead and come back in, we will start our next session shortly. If you're one of our speakers, especially our first one, would you like to come up here, please?
So we had some technical difficulties because we lost power in the back, and we don't know why, but now it's back. So if you're sitting in the vicinity of the power cord that's taped to the wall back there, try to be careful not to trip over it. Thank you.
I think we're going to need to do this again. Let's do that. That's why we did this, right? Yeah, no doubt.
All right. Looks good on this side.
Looks good over here. Sweet. Thanks.
All right. Happy post-lunch Bing Bang Con again, everybody. Can I get a woo for lunch? Can I get a woo for all the talks that have happened so far? Can I get a woo for the talks that are about to happen? Great. Love it. We have 3 more talks to hopefully fill you with joy, surprise, or excitement about computing. So let's get those started. Our first speaker loves learning about the world in its surprising amount of detail, how it works, and somehow how it all somehow manages to work. He is let me read this correctly. Says, just imagine NYC humming along in 1924 with 6 million people, 600,000 telephones that could all interconnect and 0 electronic computers. Interesting, right? Our next talk is by Jesse Chin called A Brief History of Keyboards.
Hi, I'm Jesse. Can you all hear me all right? Yeah. Cool. I'm really interested in the history of technology because it's really fascinating to me to kind of look around and notice that just about everything around us, this works better when we're indoors, but just about everything around us had to be invented by someone, right? Like someone had to invent the concept of bricks, of quadrangles, of campuses, of halls, and so forth. And it's really easy to forget even when you're trying to remember it. So one thing that I like to do when thinking about this is look at early prototypes of a thing that became standardized later. Like, have you ever looked at what bicycles looked like in the 1800s? Like, there's one standard design that we all kind of accept now, but like there was a lot of stuff we had to try before we got there. And so I did this for typewriters not too long ago, and there's some really fascinating stuff in the, whoops. Yeah, and there's some really fascinating stuff in this space. Well, good enough. I mean, you can see how many different ways there are to make typewriters if you don't know what a typewriter looks like ahead of time. In particular, this ridiculous thing like is called a writing ball and was actually used by Nietzsche to like write his manuscripts. And while scrolling through these, I came across this one picture and like it made me sit bolt upright. Like that is the keyboard I have in front of me. What is it doing here 150 years ago? And so I went to learn about this, and fortunately it's actually surprisingly easy to learn about because the inventor here, you can see, has signed his name as Latham Scholes and filed patents with the US Patent Office every step of the way. So we could kind of look at his earliest design and see where this came from. So his earliest patent is based on a piano. Basically, Latham Scholes is a Milwaukee-based newspaper editor, and like many other inventors and businessmen of the time, thought it would be really amazing to have a machine that you could use to write, since machines were getting more precise and more effective, and you could build more intricate ones. So as his model, he turns to one of the most intricate machines of the time, a piano. And you can see his initial prototype here is actually just kind of a piano. It's only got 11 keys, but as he progressed, he added the rest of them. So a later prototype included all 36 keys without the 1 and the 0 because you could substitute the I and the O for them and just kind of put the letters where they may. He quickly learned that it became more intuitive if you did the upper row backwards instead of forwards. While working through these prototypes, it became clear that like having 2 rows of keys was just not working out. So he pulled the numbers out to a top row and pulled the vowels out to a center row. And you can already see in this like really basic thing, like what those bottom 2 rows kind of start to resemble what a keyboard looks like. So this was kind of an early prototype that he sent around for testing. And contrary to popular belief, he was really savvy and invested in the success of this product, so shopped it around to a whole bunch of different people, in particular stenographers and telegraph operators, and got some advice on what should go where, what letters should get near each other, and how to make this work as efficiently as possible. And over the next 3 years, he made a bunch of different substitutions. This is what he ended up submitting to manufacturing. And for manufacturing, he ended up going with, at the time, also another manufacturer of delicate precision mechanical devices, Remington, which sold rifles. The folks at Remington got back and recommended a few additional changes. So without these changes, we would be talking about the QWERTY keyboard. And there it is, like it's off to production. Here's a model of the first production piece. Why do we still use this today? As a savvy businessman, when typewriters were first introduced, everyone used them the way he expected to be used, which was hunt and peck, right? Like you look for the key you want and you press it. But before too long, people are very smart and kind of invented touch typing. And he realized that A, whoa, touch typing is awesome. B, if I gave away touch typing classes for free, but used this keyboard, everyone would be locked into this keyboard layout with their new skills. So that's how we got to where we are today. Now I'm going to try and somehow speed run 150 years of iterative refinement of this keyboard in the next 5 minutes. So let's see how this goes. Here we have an Underwood number 5, which is the kind of archetypal typewriter. In the 22 intervening years, folks really iterated on typewriters, you know, all this cutthroat competition, and we ended up with this, which is basically, if you ask someone to imagine a typewriter, they'll probably imagine this thing. You'll see it's got, this keyboard has 2 interesting additions I want to point out. One of the major features is that the original typewriter couldn't type lowercase characters. So the hammers now have 2 characters per hammer printed on them. And there's this shift key you could hold down to shift where the hammers hit, so that you hit either the upper or the lowercase. There's also this tabular key up here. Another key feature was people kept making tables. So there was this mechanical device that you could slide wood blocks on, and when you hit the tabular key, it would move on to the next tabular stop, which was where you put the wood block. Moving right along, typewriters were one of the later appliances to get electrified because there wasn't actually that much benefit you can get from like using automatic power here, but there was some. In particular, you can see an example of kind of metal tabular stops here, like the thing that you can see the metaphor for in word processing programs now. But yeah, this is an IBM Selectric, most popular electric typewriter of its time, and it's got a couple extra additions that I want to point out. First is this shift block key. The shift key required a lot of force because you were actually pushing the mechanical thing down quite a bit. So a shift block key just kind of let you keep it locked down so that you didn't have to like hold your pinky on the thing anymore. There's also this new return key with the advent of electric power. Instead of having to manually line feed and carriage return the typewriter, you could now press the carriage return key and the carriage would return all the way to the left. We all know that there has been lots of hay raised about like whether line feed, carriage return, both, or in what order actually signify a new line. That's what that's from. Not too long afterwards, the mainframe computing started becoming really big, and people wanted an easier way to interface with these computers than punch cards, so they hooked up a teletypewriter. This here is the Teletype Model 33 to a mainframe in order to control it. And the stuff that they added in order to help with controlling these things where, well, there's this control key, since you're actually controlling the thing, and you can see a lot of these keys have marks for like what control characters they use when you press them. In particular, Control G is bell, you can see here. I'm sure our Unix aficionados know others. They also added the escape key to let you escape from whatever you were currently doing. And then as mainframes gave way to personal computers, there's like the giant block keyboard that everyone knows. Other stuff that got added because like controls got more and more intricate as things went on include this giant block of 12 function keys that do arbitrary functions, and these alternate control keys. And that's about as big as keyboards got, but that's not where they stopped evolving, because the next thing was to try and take this gigantic, hefty control device and shrink it down into 2 inches. And here's one first attempt that people can argue how successful it was, and we can kind of end up at essentially where we are today with the advent of swipe typing, emoji keyboards, and so forth. All right, that is my overview.
Thank you very much, Jesse. Our next speaker has been building UIs for 25 years. He likes explaining things with pictures, and I have a feeling he'll have some pictures on his slides. Next up is Adam Solov with recreating Sketchpad, the first GUI.
Hey everybody, I'm Adam, and I'm so excited to be here and to talk to you about Sketchpad. You good on slides? Cool. The first computer program that had a graphical user interface. Well, let's back up. So in 1962, if you would ask somebody what the user interface was to a computer, it was a human being who would take your stack of punched cards or other input, and their response would be, come back tomorrow and get the answers. So it's kind of amazing and hard to believe that also in 1962, there is this kind of a computer interface in exactly one place in the world. In MIT Lincoln Labs, we can see somebody using a piece of software that is recognizably software. There's a live screen showing the state of some process. There's a pointing device where they can directly interact with things on the screen. And there's buttons and commands to take actions on it. The program that you're looking at is called Sketchpad, and it was created by Ivan Sutherland, who is a PhD student, as part of his dissertation. And it's a piece of software that there was sort of nothing like it before, and not anything better than it for 10 or 15 years. In today's talk, I want to pass on my excitement about Sketchpad and hopefully get some other people who are excited about it. I want to show you a live demo of what Sketchpad could do. I want to talk to you about some lessons I learned while making a sort of new version of Sketchpad that will run in a web browser so you can actually play with it. And I want to talk about why it's worthwhile to study old programs, especially old UIs. So let's start with a demo. Here's my little instance of Sketchpad running in the browser. And Sketchpad was a program for making precise diagrams, things that needed to be mathematically correct or that would be difficult to do by hand. You'd have to like measure and calculate in advance or use drafting tools. But Sketchpad's goal was to make it much easier to generate those kind of precise drawings. If I can see my mouse in the sunlight. Cool. All right, so I'm gonna draw a rivet, and I'm just gonna start by drawing some lines here. And I'm gonna draw them pretty imprecisely because I don't have to draw them precisely because I have a computer. So what I can now do is ask the computer to make these lines perpendicular to each other, and it'll just kind of nudge around the points until it does that, which is cool. Now I need to find the center point of this nice rectangle that the computer has made for me, which I can do by drawing the diagonals. And now I want to make the head of the rivet, which should be an arc centered on this middle point and going out to this end of it. And now you can see, I didn't calculate this in advance. I've been really sloppy. I really want this arc to end all the way over here. So I'm just going to tell the computer, hey, I want the arc to end all the way over here. I'm going to kind of nudge everything around until all the nice mathematical properties of my diagram work. Now I have a part that I'm trying to build that actually needs a rivet in it. So I'm going to come to my other picture, and now I'm going to make a new instance of my rivet, and I can rotate it. And what I really need to do is zoom it smaller. And so now I can use my first drawing as a symbol inside another drawing. So I want to just pause there to say, it's kind of amazing that you would invent the very first GUI ever and not just do like MS Paint. You'd actually like you'd do a constraint solver, and you'd invent like a component and instance system. It's a really cool and powerful program. So let's talk about what it did take to implement this and what I had to recreate. So in memory, we're going to represent our drawing as a bunch of individual blocks, chunks, pretty much like structs, but Sutherland called them blocks. So we've got a point block, and it knows its x and y coordinates. We've got a line, and we've got a circle. And we're going to imagine that this line and circle depend on this point. It's one of the coordinates that they use. So he invented a data structure that he called a hen and chickens. We today would just call it a ring, that connects all the items in some children that share the same relationship to some parent. So this lets you say, if you're doing something with the point, this lets you walk through to all the shapes that depend on that point. If you're doing something with the line and you need to know its start point, you can walk through the ring to find that. This is an efficient way to represent that. Now you get to doing some operations. Let's say the user wants to delete the point, and so we also need to delete the line and delete the circle. Well, you can start to write that code and you run into a problem, which is that in this ring, you have different types of things. So how do you know which operation to apply, the way to delete a line instead of the way to delete a circle? The first version of this program had the equivalent of a big lookup table and inline branching, and that got annoying as he added more stuff. So Ivan Sutherland invented this idea he called generic blocks, where he would connect each concrete point in the drawing to this generic block called the points block that has another ring that goes to all the points. And similarly for, line is connected to a lines block, circle is connected to a circles block. So now when you want to write code that deletes a point, you can say, go to each shape, and just don't worry about what type of thing it is. Just ask its parent how you delete a shape like that. This diagram isn't presented exactly in the dissertation. It's not this clear if you read it yourself, but if this looks like object-oriented programming and he just invented it as an offshoot of his other thing he was trying to do, that is in fact historically true. Alan Kay has said that it was reading this paper along with one other in 1966 that gave him the idea for what would become object-oriented programming and Smalltalk. Again, just sort of on the side of this thing that he's trying to do. He also became, I think, the world's first UI programmer to get kind of lazy and want to refactor everything every time he added a new feature. So he says that he's become reluctant to write any specific programs for any specific jobs, because you could just sort of keep rearranging the system until it's really easy to do. It also raises one more question. If a circle is connected to a parent that's the circles block, what happens if we keep going up that chain? So he invented the world's first inheritance hierarchy. The circles block is connected to a thing called topos, which is all the different shape types. And that's connected to universe, which is everything in the system. It's like a basic object. And then he asked a theoretical question, which is, well, universe needs a type too. We shouldn't just have one special thing that doesn't have a type. And so he speculated it really ought to be the case that you could just keep going infinitely up and create more and more abstract things. Very generously of him, he decided not to do this. So in this dissertation in which he invented so many other things, he left at least one thing for later people to come back and invent. And if this looks like meta objects in Ruby or in Common Lisp object system, he basically had that idea and then was like, maybe somebody else can do that. A fun aside, his PhD advisor was Claude Shannon, who had invented information theory and the fundamental basis of electrical circuits in his master's thesis. And people made him come back and do a PhD dissertation as well. But he was a little picky about his graduate students. And so he came to see a live demo of Sketchpad in an early state. And his student had invented GUIs, had invented object-oriented programming, had this cool thing. And he was like, why doesn't it have circles? I really want it to have circles. And Sutherland explained to him, nobody has an algorithm for calculating the points on a circle fast enough to be in this program. And Shannon apparently was like, that's a bullshit excuse, figure it out. So Sutherland had to go work with mathematicians to find a new algorithm so that he could draw circles so that his advisor would come actually watch the demo and pay attention. So if you're a graduate student, hug your advisor. If you're a UI engineer and you've had a stakeholder come and just be like, could you just add this one feature? It should be pretty easy. You're proud of a proud line from the very beginning. There's one other thing, one other fun detail here. When you see the original videos and screenshots of Sketchpad, the lines have this warm, fuzzy impreciseness to them. And there's a reason for that. He was using a really old CRT, and moving the laser for the CRT was really slow. And each pixel after it lit up would take a while to fade back. And those two things together meant that if you drew the picture kind of like each pixel in one line and then each pixel in another line, you'd get this effect where different parts of the screen were brighter and dimmer, and you'd get a really weird strobing effect, and it hurt everybody's brains, and they couldn't use the program. I'm not going to show it live, but if you just sort of imagine this, but then rotating at 60 hertz, it's really painful. So he invented an algorithm he called twinkling, which would draw the points in the picture in a sort of pseudo-randomized order. And it gives it this effect of it's less precise, but it's warm and fuzzy. It feels like old analog electrical equipment. I love it. So I, in my recreation, made an HTML canvas element API that would kind of draw this slowly and fuzzily. And it's, on the one sense, a complete waste of time. And on the other hand, it makes me very happy. So I want to leave you with some thoughts on why we should study old UIs. One professor taught Sketchpad in an intro course, and some students came up afterwards and said, "What's so cool about that? Isn't that just what computers are?" But they're not. Everything about the world of computing we work in is contingent. It's a decision that somebody made. They might have made it right or wrong. The ones that survived to today might have been the good ones or the bad ones. It's worth studying the old things to find out which historical mistakes or which historical precedents are worth revisiting. Finally, I love the complete optimism of people who are doing something for the first time. This is one of the section headings in Sutherland's dissertation, and I'm afraid of needles, but if I were going to get a tattoo, this is what I get a tattoo of: the as yet undreamt of things that will be displayed. Even today, 61 years later, there are still undreamt of things that are yet to be displayed. And that's what I like doing. Thank you.
Thank you very much, Adam. Our next speaker works in R&D in image technology and enjoys adventures, eating things, and meeting people. Once as a child, he swallowed a bunch of nickels, which gave him the memories and powers of those nickels. Unfortunately, the nickels knew very little about the natural world, so afforded little benefit. They were not dimes. Our next speaker is Phil Warren, and the talk is Images from a 1970s Typewriter.
All right, let's see, which of these do I plug into? Whoop. Okay. And there we go. Hi, I'm Phil Warren. Oh, I'm not getting presenter notes, I'm sorry. Let me see what's going on here. And let's try that again. Okay, I'm Phil Warren. I'm a color scientist and computer vision specialist based in Los Angeles. For my day job, I help film, television, and video game companies capture and display imagery. And in my free time, I do pretty much the same thing, but stupider. Now, I wanted to change things up recently. Sure, we see dazzling images on a huge silver screen. They make Nicole Kidman's mind real, and yet I crave something more. What if there were a way to capture an image and emblazon, emboss, ink, or otherwise commit to a physical medium like a sheet of paper? A ridiculous dream, I know, but surely there's a way to put an image on paper. Now, the ink alone would cost nearly $10,000 a gallon, so this is a fool's dream, but if some magnificent machine could do this, we could even make a flip book and create video. And that led me to conclude that obviously we need to use a typewriter to do this, from 1971, and then find a way to make both images and video with it, which is the problem we're trying to solve today. Today, we're going to get images from a 1970s typewriter. Now, the first phase is simulating our idea poorly. Now, I'd made works of art for a show at the Dark Art Emporium 2 years ago where I downloaded 500,000 NFTs, more fungible than the name implies, and used frequency analysis to recreate works of art out of NFTs. What if I did this with typewriter glyphs instead of NFTs? To accomplish this, I used a package I absolutely love with a team on GitHub that has been exceptionally responsive to requests. It turns an image into a mosaic while respecting curves and textures. This image collage maker has a GUI to experiment with, but then it has a command line interface with Python so I can smoothly integrate it into code, imperative if we want to do video. So first I wrote a quick little script that converts a font pack to images. It uses nothing more than Pillow, and it names each image with the ordinal Unicode pointer. Now, the ordinal numbers will be very important later. Now, we're going to take this input image because I love it desperately. We run it through the command line interface with a simple Python script, and success. Looks like we can, in fact, use Python scripting to generate a black and white image using this technique, which also gives us a list of the letters used in the order they were used to be typed and recreated on a typewriter. But we can do better. So the second phase is texture in the real world. Now, a little bit about our typewriter. I'm using the Selectric typewriter, which was just discussed. When it came out in 1961, it changed the world. By using a whirling, bobbing ball-like element called a type ball, this single-handedly changed typewriters and computing forever. This type ball not only sped up typing speeds by tenfold, it also, for the first time ever, allowed for typefaces to be changed out of a typewriter simply by replacing the ball. Now, a brilliant optomechanical engineer, Joseph Ballas, had emphatically presented me with a project last year. Programmer Sam Ettinger had finally cracked the nut. Selectric balls could surely suddenly be 3D printed. Could we design our own? Surely it would be madness to try and design a type ball that wasn't ASCII characters, right? And the Adventurers Club, specifically a representative named Andrew McGregor, took an interest in my project. Runic Elder Futhark, a Norse proto-language, would be in high demand in his Scandinavian circles, so I designed some balls, printed them up, and he showcased them in Oslo. It worked. And from this limb of the project, I got a working Selectric 2 and a connection with a resin printer. So I can extend this. By feeding a handful of texture font packs into the mosaicing algorithm, I can see which ones were used the most. I limit these to the top 62, leaving space for 26 characters so we can still type, and now we have a custom ball. Now, after 36 hours, oh my God, rendering this to printable geometry, we have a workable glyph ball that can type textures. And don't forget, we recorded the decimal ordinal characters in an earlier step. With only a few lines of Python, we can now generate a cipher in which earlier ordinal characters are translated back into the keystroke that would generate it. This means a human hand can now type this cipher, and the custom glyph ball can type the intended picture. Remember our alphanumeric piggy from the last phase? He's looking much better. It looks like 62 custom glyphs can create an image of a higher fidelity. But we can do better. Our third phase, color. Remember, when we put pigments on a real-world object, we don't see the color the pigment is, we see the color it isn't. Our eyes receive the photons it bounces back, not the photons it absorbs. That means that the more pigments you mix, the less photons bounce back. We call this color model subtractive, where mixing all colors make black. When dealing with modern display tech, we generally think in additive terms, where mixing all colors makes white. And this makes thinking about real-world pigments digitally complicated. Now, normally, we use 4 colors, cyan, magenta, yellow, and black in the subtractive model, but as typewriters can do, at most, 2 colors, we're going to set that as the limit for today's project, 2-color imagery. Now, Technicolor tried to pioneer a 2-color model in the 1920s. As they frantically researched how they could do a full-color projection, they came up with some stopgaps to present a sort of pseudo-color to audiences. They figured out that by using 2 colors, they could sandwich the film strips together for a subtractive model. In Technicolor's process 3, they determined that if you only use 2 colors, you should use red and green. Red dye will help reproduce skin tones. Green dye will help reproduce foliage. And blue? There's no need for blue. Perhaps you misremembered the sky anyway. In fact, fuck the sky. Now, King of Jazz is my favorite example of Technicolor Process 3, possibly because it's the only full film in this format I could find. To simulate the capture of that 1920s camera they used, we split an image into 2 channels. Now, as all images are nothing more than m by n by 3 arrays, we just multiply the same input by the RGB values of each given glass filter we're simulating, and the result is what the emulsion surface would have exposed. Next, as before, we just run the Python script to convert to mosaic of glyphs. Next, we simulate the dye imbibation process the film would have gone through in the 1920s. Instead of washing out the soft gelatin in the film, which was black, and replacing it with dye, we use Python to replace the black and with either a salmon red or a mint green, leaving just enough blue in the pigments that when layered upon each other, they create something black adjacent. Then we mix the two resulting images in a subtractive process, which is simple multiplication in Mathland. So we go from to this. Success. But we can do better. Our fourth phase is making this electric more electric. Now, around 1983, there was a security leak at the US Embassy in Moscow. When everything was torn apart, the US discovered magnetometers embedded in their Selectric typewriters. When depressed, each typewriter key broadcasted a small electric signal to the KGB, the world's first keylogger hack. We can literally reverse this process, sending a small electrical signal to an electromagnet, having it create keystrokes. Now, this would make a typewriter that types by itself, powered by solenoids. Now, programmer Alan Wilson has already cracked a method to automate the Selectric 2. This converts the typewriter into a teletype machine or a proto-printer. Now, my partner in crime in this phase, Joseph Ballas, and I are currently at work on this. But can we do better? Yes, we can. So, phase 5, pipe dreams and future goals. What if we could embed an SMS chip, then text the typewriter? What if we embedded a camera for a surprise selfie? What if we added voice to text as an accessibility feature? What if we hooked up an electroencephalogram and made it brain-powered? And now we see the fruits of my project. Now, this is a flip book simulated at this phase until the typewriter automation gets working, and we see each of the 4 phases. And that's what it is for now, but please slide into my DMs on Instagram, hire me, or get hired by me on LinkedIn, grab my phone number after the talk. Let's chat more image technology. Cool.
All right. Thank you, Phil. By the way, if you haven't noticed his blazer over there, it has a nice mosaic pattern. You should go check it out up close. So before we wrap up for this session, I want to talk about unconferencing a little bit. So we've talked about the signups over there on the whiteboard over in that corner over there. But in case you don't know what unconferencing is, it's sort of like improvised conferencing. So propose a session, stick it on the board. Whoever is interested in coming to it can come to it. So it's very like planned ad hoc, or slightly less ad hoc because we're planning it now. But you have pretty much like when unconferencing happens, just the whole space. So if you want to also put like a location on there, it's just like, hey, we're going to meet by the stairs, or we're going to meet wherever, do that. And then that's when unconferencing will happen, not next session, but just after that. So if you have any questions, ask one of the organizers, and we're on to our break, unless you have something to add. You have something to add?
Yeah, so we now have a 10-minute break. There is more lemonade and iced tea over there. We seem to be out of water, however. If you really need water, talk to an organizer and we'll let you into the building for the water fountain. Otherwise, it's time for the 10-minute break. And if you're speaking in the next session, please come up for your AV check. Thanks.
And we'll get started in just a minute. What? Yeah, woo! Two small notes before we get started on this next section. Just a reminder that although we are outdoors, masks are preferable, especially if you've been sick lately or anything like that. There's masks available over at the registration desk if you don't have one. And number two, Lindsay was wrong. She told me to say that. She's very sorry. There is a water fountain. If you go through these doors here, which should be unlocked, you go all the way through the building and out on the other side. Just outside those other doors, there should be a water fountain. So I'm sorry that we don't have enough water over there. If you need to refill your water bottle or something, you can go through. Am I not loud enough? I'm not loud enough. Hello. But I don't want to, people were complaining that there's popping if you're too close. So we're trying to find the right balance. All right, without further ado, let's get into this talk star, not a talk, a musical number. Taylor is mayor of Taylor.town and certified connoisseur of crap. He tinkers with writing, learning, time, design, software, ideas, and humor, and also John on guitar. Come on up.
All right. Thank you guys for coming. Just want to give it to you. Good news. 2 dudes proved 1 and 1 makes 2. True before, but now it's true. And it only took them 2 to the 2 to the 2 to the 2 words to do her. Cold may have made men equal, but didn't make them even. Men are violent, God's gone silent, there's only numbers to believe in. But lawless numbers plague the world in 1882. You can't corral your digits in tidy little groups. Hyperbolic, hypothetic railroads turn each day to minutes. Meanwhile, mathematicians push that calculus past its limits. The frontiers of math surpasses wilderness and Indians. Hell, when a song's gone this wrong, the sarsaparilla's gone non-Euclidean. Folks sought the rules for truth, they prayed they could be tamed. The laws of God awed us once, but now it ain't the same. Cantor sets up set theory, others analyze analysis, but all are buffed by infinite infinities, self-referential paralysis. So Freaky wrote the rules on quantification and inference, and suddenly the wilderness is filled with these mathematical logicians. Logicians are a funny folk. They care about correctness. Historically, men, Socrates' mortality till math wrecked it. Russell rustles Freaky's feathers with an impish little loop. Sets that don't contain themselves, they're bound to come unglued. If barbers only shaved on shavers, who's there to split the hairs? If logician's dog only barks at strangers. Can it bark when no one's there? This rigmarole probably needs a lot more rigor. We got logic in our pockets. We got symbols on the trigger. Among the swamps and crocs and paradox, Hilbert yearns for terra firma, formal systems, rules, and axioms. Let's polish all those terms up. So Hilbert put the bounty on all truths pure and vast, and wild in the wilderness with a cathedral to hold the maths. They bet success on sets of sets, wrangle barbers using types. This stuff is good as it gets. Right minds to make math right. We got two dudes to find what's true. Bang, bang! 2 shots from a revolving revolver will solve her. Every human tongue can say everything and nothing, so we invented math to sort the 2 things from the 1 thing. But if math's specific, it can't say arbitrary anythings. If it's consistent, it insists on saying something. Because any formal system mixes symbols, truths, and inferences. For instance, arithmetic is consistent, but skips soft descriptions in pursuit of precision. Listen, alluring, elusive, mutually exclusive, you cannot beat this. Gödel found Faust in all formal systems choose consistency or completeness. Watch your back in the mirror, logicians fear them when they hear them. Kurt Gödel's 2 completely insane incompleteness theorems. Too dumb to utter, what a fun introduction. Here comes bullet 1 straight from the gun, son. For any consistent formal system that articulates arithmetic, one can find the numbers to encode its truths inside it. Turning a Gödel number into an arithmetic operation, make statements about other equations to the system's dismay, son. So formal systems talk about their paradoxes. Just say the statement's false to puncture logical locked boxes. Diagonally evade direct self-reference. Who meet correction? They're incomplete unless they have something to say for it. God's gone now, ain't nobody to pray for it. For a cold, cramped confession booth, cathedrals cannot hold the whole of maths without holes in its roof. Bullet 2. If a system is insistent that contradictions are non-existent, then that's a false statement, and the system's inconsistent. Good old Gödel's eternal hurdles as turtles on turtles. Kurt murdered math in the bathtub, making logicians' blood curdle. He ripped a page from Principia and wiped his glasses. Scrawl small proofs on the stall walls, hurting and hurling from the gas. From cradle to casket, basket cases in every math class. Take a seat, son. You missed your last chance to pass. Gödel. Hilbert got 99 problems, but a proof ain't one. Don't die on that hill burning, goodwill hunting in the sun. Theorem after theorem, put down without a fighting in. Provably unprovable purgatory ad infinitum. Well, the Wild West bested the best of us. No foundations for our fodder. We'll settle down and build a town for our grandsons and granddaughters. We'll prosper, share the gospel, share our wealth, our hunger too. The city of cement and steel will rise up from those ruins. Charles Babbage dreamed of machines that could conjure up some thinking, but it took a lady's brain to think of machines that could do some dreaming. Lady Lovelace listened and heard music in those digits. It ain't a crime to paint by number once or twice, or is it? Ada envisioned men and women aided by such precision. No work, no war, no worries. Machines handle heavy lifting. Letters leak from lightning wires sparked by dots and dashes. Ditch your horse for a Morse code, son, to telegraphs in fashion. Fast forward to the Great War, where we create great calculators capable of storing words for warding off invaders. Cathedrals collapse under carpet artillery, but Alonzo Church still stands, hand in man the lambda calculus, an early kernel of computer programs. Electric contraptions, get the gears turning. Here's turning. Learn machines to keep Europe from burning. Enemies telegraph this cryptic crap behind our back, but we got magic, man. That cryptography's cracked. With ample tape and patience, computations say the same things. No oracles, no miracles, no ways to fake the faking. Miraculous task, Turing tasted the forbidden fruit of computing, and in that oracular orchard, he died by an apple of his own undoing. With the enigma egg unscrambled, nerds tilt that axis backwards, extract entropy into information, and protect our precious passwords. Eyes open, no wool pulled, shorn from the lambdas. Punch card pulled from the looms, the mind no longer knows what the hand does. Soon thereafter, transistors supplant fragile vacuum tubes, growing faster, insisting that chips can shrink by factors of 2. Damn, those busy beavers can be a lot to top. But the halting problem never told us when to stop. Computers continue to secure and wreck our cities, cracking codes, building bombs, and crunching heat-seeking trajectories, wrestling the devil with the best of intentions. The road to hell is infested with null pointer exceptions. Integrate circuits into chips without dip microprocessors, little cities built from the sand. You better lay off the sauce, sir. Good news, grace will guide you due to the moon. Soon, von Neumann CPUs will fit in nanometer grooves. When Johnny Neumann was a boy, math was but a toy to him. But now he's a man, a maniac with an ENIAC and still a spoiled kid. After patching paradox, slapping axioms on algebra, after cracking the quantum, von Neumann caught that little computer bug. He builds the bomb, tries life, defines what games are made of. Each machine invents the architecture of process and information, found that by storing instructions and data together in memory, each machine can emulate anything without much reprogramming. But before von Neumann got on board that train to hell, he received a little letter from that rascal Kurt Verdell. If you try to build a metropolis, you know we'll topple it. Since every possible program fits in countably infinite space, place them in sorted order and give them numerical names. You can imagine a program that scans and plans faster than man can, but can that programs faster than proofs expand, man? Consider this tricky bit. If such a computer can exist and can go quick, they can query the answer key in the back of the book faster than a math whiz can pull out his abacus. Time out. Halting problem need not be heeded, if indeed we proceed with reasonable speed, and we quit when needed. These decision problems could solve oddballs within practical limits, if checking a problem and solving it stay within limited distance. This letter discovered decades later, folks would find that Kurt Verdell defined the E and NP landmine ahead of his time. To be or not to be, to P or N to P. Can non-deterministic polynomial time programs run efficiently? PNP asks if a vast rift between questions and answers exists. It seems like solving is harder than checking, but you'll have to check with your therapist. PNP posits whether all forks and all roads lead to Rome, or whether you'd be better off just staying at home. PNP asks if you can run programs backwards efficiently, or if doing so makes big, oh no, complexity. PNP lays cement for stable cryptography. Without sufficient ciphers, it sucks to be lock and key. PNP sounds simple, but kills countless careers. The naughtiest doggone problem gone unsolved for years. To be extra obtuse, diagonal proofs are of no use. Up crap creep without a half a paddle in a leaky canoe. $1 million bounties out for any person with proof. Prize the millennium awaits you if you can manhandle that truth. Meanwhile, Moore's Law means more and more slop. Gigahertz in our shirts and teraflops in our socks. Computers play chess while humans play checkers against pigeons. Even Lisa Dahl gets creamed by algorithms younger than infants. If the computers continue to do this, then humans are useless. The soothsayers crying doom, the theorem provers proven ruthless. We mined a land to build city on a landmine. Mine's blown, no diamonds. It's bound to be a bad time. Math's last answers may be unattainable. Man's match with machines may be unsustainable. But such is life as flesh, blessed with the best questions, and at least a seat at the table.
Wow. All right. Up next, we have Huggable Data, Making the Ephemeral Last Longer with Textile Data Viz by Aldis Elfersdotter. Aldis is a PhD student in management science and engineering at Stanford. She studies how to manage the clean energy transition among global firms and the challenges with self-reported data, carbon accounting, and ESG ratings. She recently had the pleasure of taking Quinn Dombrowski's class on data visualization with textiles and made a PhD dress to visualize her 3 data sources in dress form. Come on up.
All right. Thank you so much for having me. This is my huggable piece of data. I can hug it. And I'm going to present on how we can use textile data visualization to potentially make our digital data last thousands of years. First, I'd like to thank Quinn Dombrowski, the teacher of my class, without whom I wouldn't be here. So thank you, Quinn. So I want to do a little stretch and also gauge the audience for who prefers hard drives. If you lean right versus cloud data, lean left. Maybe raise your hands. Right, left. So the thing that brings us together in this digital age is that we are all increasingly storing our data in cloud devices or digital devices. And that kind of storage is subject to rapid change. If you think about the history of humanity, it's like and in this past year, it's like AI, data visualization, all this Google Cloud storage, you're running out of storage, buy 2 terabytes for $20. It's like everything is happening so quickly, and maybe even hours ago you were asking ChatGPT, what's the bug in my code? So if we have this rapid changes, it's very unpredictable what our future of data could look like. On top of that, we could get hacked, your data could get corrupted, there's planned obsolescence on a corporate scale for different iPhones having different charging points, for example. And it's expensive to maintain the physical spaces where all of our data is getting stored around the world, not to mention also harvesting the raw materials for this. I ran into an example recently about file obsolescence, where they literally said in their website update that any files you saved as this particular form of SVG will never be recoverable, and shape data is irretrievably lost for these file types. So that's what we're dealing with in this rapid changing age with each new software update. And moreover, the extent to which we rely on our digital systems these days is crippling when they fail. I was in the airport that day, the right 2 pictures are mine, when United, Delta, American Airlines were grounded because of a CrowdStrike software outage. And all the cancellations and everything, people were stranded. So we're like, what do we do? Also, what would we do if our hard drives got smashed? Well, we'd be left with a pile of electronic scraps and rare earth metals, probably not the memories we were looking for. Whereas if this just got smashed, I can iron it out and take a look at my PhD data again. All right, so all of this building up the case for looking back into the past at what our ancestors did to take our data out of our computers and into textiles, before computers even existed. So the oldest example I could think of textile data viz is quipu, the system of knots used to record information by the Incan Empire 5,000 years ago. And the amazing thing about this is that we can touch and feel and even decipher this data today. So it's pretty proven that these types of data preservation are longer lasting and easier to preserve compared to modern day, flip phones. I can't even access my flip phone data from 2010. And in more recent history, there were even ways of using textile data visualization in World War II as espionage. So knitters would encode information about battle updates and send them in the form of sweaters to prisoners of war. And the way they did this was that in the yarn pieces, there'd be different knots. And they would associate each different type of knot with a letter of the alphabet. So in case you're inspired by any of these examples, I encourage you to try some of these how-tos and use your creativity to guide you. But basically, you can revisualize any 2D plot in the form of your choosing. If you already know how to do cross-stitching and sewing, or if you want to learn how to embroider and knit and weave, these are all possible ways of visualizing your data in textiles. So I have two examples that also make social statements in the way that they are turned into craft. The rightmost example is a cross-stitched form of a bar chart. And I bet we would all underestimate the time it took to make this chart, which is partially the value that it's conveying of what's traditionally seen as women's work or hobby craft being devalued. And the point of the data in there is that women do a lot more unpaid labor than men. And now you don't have to be a woman to make these statements out of data into crafts. So I encourage everybody here to try it because it's really cool. On the right, we have beadwork as DNA, which makes the case for indigenous data sovereignty, turning information, computerized data about the DNA of diseases affecting indigenous populations into a woven burden strap, saying this is the data we carry. If you want to go further, you can even look at different dimensions of the material that you're using to create your visualization, such as texture or pattern or smell or direction of the yarn and different patterns. And you can choose various pieces of information to encode. So the bracelet image you see here is actually a large text data visualized in different patterns, and different quotations arise in the different patterns. It's also important to include metadata for decipherability unless you are doing espionage. So this metadata is held on the web, which is itself ephemeral, but it's very cool because you can zoom into the image of the bracelet and see what quotes emerge. Okay, so for this dress, I wanted to show you, I forgot to include metadata labels of like what each panel has, but I'll be your metadata today. Here we have in the front all industries from 2010 to 2020. And since I'm interested in self-reported data, the green bars represent the potential for greenwashing among the companies within this industry whenever they put out a green signal of self-reported carbon data. And then we see trends in toxicity in the purple asterisks, where you see peaks over time in how many toxic chemicals these companies are reporting to the EPA as being released to the land, air, and water. And we also see some inflation in ESG scores over time for environmental social governance performance. And you wonder, what's the basis for these ratings and this improvement? And what I love about this is I used to be able to wear it before I washed it and it shrunk. And then you can hug it, you can, if you made a blanket, you could sleep under it. And I wouldn't be able to do this if I had showed you, for example, a different form of physicalization like printing, where you'd see 1,000 sheets of paper like unwaddling, and it would be indecipherable, unmaneuverable, and ungraspable of what's the main points for takeaways. So all this to make the case for looking a little bit further back into the past at the most successful forms of data preservation as we think about how to preserve our digital data today. And I look forward to seeing where your creativity takes you. Thank you.
Thank you. Next up, we have Keyboarding Ain't Easy, What Not to Do When Building a Keyboard by Liz Frost. Liz is a, I don't actually know how to pronounce whatever word you put in here. Computer tutor? Teacher? Toucher. Liz Frost is a computer toucher, cable organizer, and colorful equine. She lives in Vancouver, British Columbia, and works for the company that wakes you up in the middle of the night. Find her online at Still in Beta and ask to see pictures of her pets.
Hello. As Erdy said, I am by day a infrastructure engineer, and I am not going to talk about that at all. Instead, I'm going to talk about that time I set out to build myself the perfect keyboard. And if you've looked at the title of my talk, you know that I failed. Why? Easy. Hubris. So this started with DSA Dark Magical Girl, which is a set of keycaps that I found online one day, and a friend of me encouraged me to buy, and I absolutely fell in love with. But unfortunately, these are key caps, not a keyboard, and you need a board to put them on. And unfortunately, this was the keyboard that I used at the time, which is, it was suiting me very well, but it wasn't fancy. It wasn't cool enough. So I spent a bunch of time researching keyboards, which is one of those holes that you can basically dig forever in, and I discovered this thing. This is the ErgoDox Infinity, and it had a bunch of features that I liked. It was split, it had USB-C, it had these cool little screens in the top that you could do cool things with, but it was missing a couple things. It didn't have the RGB that I wanted, and the connector was on the right-hand side instead of the left, and since I'm right-handed, I wanted to be able to only have the left-hand side so I could play video games. But it did have one feature that was really the beginning and the end for me. It was open source. So plenty of people have already talked about what I learned today is pronounced KeyCAD and not KiCad. But the way it basically works is you have this symbolic representation, and then once you've got that, you can physically lay everything out on the board, and you can only kind of see it. These lines are called the rat's nest because you need to play this game a whole bunch and figure out how to connect everything together, and eventually you get something that looks like this. And this is real. This is from the board that I partially created. Usually when you are adding those gamer ergobleds to a keyboard or anything else, you use these. They're called WS2812s or NeoPixels if you're feeling fancy. And the way that they work is, if you've ever seen a long strip, the way that works is that they pass data along from one to the other, which makes them very, very easy to connect because you need to put power in from one, power out to another, data in, data out, you make a long string, it works great. I decided for whatever reason that I was going to do this instead, which is a bunch of individual LEDs, all of which need 4 wires going to them. And this is fine if you have a matrix, but is with nothing else, but is kind of a pain in the butt if you have, for example, got a bunch of keyboard switches and stuff in the way that you need to route around. But I did do this. And then I got this lovely email from the people at the PCB company who were just like, hey, so you used the wrong settings when you were designing this board. Because it turns out in KiCad, you need to very carefully add, this is how much my PCB manufacturer can drill. This is how big these lines can be. And if you were, for example, to just sort of assume naively that all of these numbers would always be the same, you might have to start your entire keyboard over again and reroute all of the lines again. But these beautiful boards did eventually arrive, and They have I paid extra for the little stencil on the back, which is very cool and helpful for soldering. But this is, you can see these little blue squares at the top. One's labeled D-, one's labeled D+. These are resistors. And when you're zoomed in like this, like you are at a computer, this looks like a totally doable thing to do. But when you actually get them, they look like this. And if I zoom out a little bit, this is a micro SD card, and I took this photo with my USB microscope. So this is the size of component that I'm working with. This is my picture, by the way, because I did do this. And this is what surface mount soldering is supposed to be. You can't use like an actual like soldering gun stick thing. And you see how they automatically sort of align themselves and like surface tension pulls them into place and it looks really magical? That doesn't actually happen in real life if you don't know what you're doing. So, and even better, you can only use the stencil once because it requires the board to be flat. Once you have added all of those components to the board, you can't use the stencil anymore, so it doesn't fit. So you just have to sort of unsolder the chip very carefully and then like put it back on and like try to get it into the right place. People make this look very easy, and it very, very much isn't. Even better, this is the LED driver, and are those pins on the side connected? I don't know. Do you know? So this was honestly a high watermark. I don't think I ever got this many LEDs working together again. And eventually, I went all through this list of things that might possibly be wrong. I have this cool setup where I felt like a cool hacker because I had like a Raspberry Pi for the serial, and I had like the programmer for debugging, and I had the logic analyzer for the I²C, and there's like a bottle of rubbing alcohol, and it looked very cool, but it didn't work, and eventually I give up. By which I mean, of course, I started over. So this is a STM32 Nucleo, which is a development board for a STM32. It is pre-soldered, which was a very big deal for me. It has a built-in programmer, so I don't need to add my own sockets. It was an STM32, and importantly, the chip on it was available because this was the height of the chip crisis. Did you know that people scalped microcontrollers? And STM32 was really important because I wanted to write a new firmware for this keyboard in Rust. And if you don't know why I wanted to write it in Rust, you clearly haven't talked to any Rust programmers. By the way, this is Hubris the concept, not Hubris the Rust real-time operating system written by Oxide. But if you work for Oxide on call me. It didn't have a USB port, but that's okay. The pins for it were broken out, and so I could connect them properly. And here I am using one computer on the left as the USB device and one computer on the right to actually program the USB device. This was deep in me trying to write my own USB driver because the library that I was using didn't actually have one for this particular chipset. What about my RGB? Well, I bought one of these from Adafruit, and it is pre-soldered, my new favorite thing in the world, and I could plug it in and program it and make sure that the problem was my code and not the device itself, plus I can make pretty rainbows. And eventually I could connect that code that I now knew worked to this board and discover that maybe I shouldn't have just assumed all of the LEDs that I bought for $10 off AliExpress worked perfectly the first time. This is what I call the depth-first engineering approach. I discover something, and I just sort of work my way down deeper and deeper and deeper until there's nobody in the world who could possibly assist me with anything else. This list literally does stop because at a certain point, Google Slides won't let you indent any farther. So what I basically learned is that you should not write everything all at once. You should prototype things. prototype, 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 which basically means I reinvented not doing waterfall programming for myself from first principles. And I completely overshot getting into keyboards, which normally for most people means, oh, maybe I will take these switches apart and I will oil them, or maybe I will buy a new keyboard. And I was like, maybe instead, I will learn how to write drivers for a real-time operating system so that maybe eventually I can have a keyboard. And in the end, you know what I did? I bought a commercial one because I needed a keyboard and I got a stipend from a new job. There is a more detailed write-up of some of the earlier steps on this on my blog, blog.stillinbeta.com. Co-host is where you can find me. That is my email address. That is my Mastodon. And if you are a professional colleague and you are seeing all of this social media that I don't talk about at work, no, you didn't. Have a good one.
Thank you, Liz. Up next, we have The Perfect Blend, Reverse Engineering a Bluetooth Protocol for Better Smoothies by Ryan Mast. Ryan is a computer engineer working on open source projects to make the electric grid more reliable. His interests include software security, niche video games, and reverse engineering audio-video hardware used in live productions. Watch out, con freaks. Welcome up.
See. All right, there we go. All right, so it's great to be here. Excited to share with you my journey reverse engineering a Bluetooth-enabled blender. So this is the NutriBullet Balance, and it is a Bluetooth blender that is primarily controlled through an app on your phone. So the app on your phone lets you get like the weight of the built-in scale and measure ingredients, as well as pick what blend setting you want to use, so like a sequence of blend on for a bit, then off. And it's a nice blender, but there are some issues I had with it. So the minor ones were that it doesn't remember what the last blend setting you chose is, so each time you have to open the app, pick the blend setting again, and the pulses, it doesn't quite turn on and off enough to dislodge food that is stuck in the bottom of the cup. So it'd be nice if you could customize it a little bit. But then I got a new phone, and the app stopped working. So on the left is my new iPhone, and on the right is my iPhone 6 running iOS 15. 15. And as you can see, my new iPhone cannot find the blender, whereas my old one is able to find and connect to it just fine. And if we expect the manufacturer to do something about this, well, the last update was 4 years ago, adding iOS 13 support, so we're on our own here. Now, my setup looks something like this. So I had my phone, the blender, and then they're wirelessly connected over Bluetooth. Maybe not outdoors, but you know. So since this is a connection-oriented protocol between the blender and the phone is acting as a Bluetooth central. And it basically is scanning for devices that advertise their presence, and then it can connect to them. The blender, on the other hand, is acting in the role of a peripheral, which sends out advertisement packets to nearby devices that might want to connect. So I want to know what data is getting sent between them, and my first thought was the easiest thing to do is just install an app on your phone. So I found an app called BLE Scanner, and then there it appears right on the list, so I can connect to it. And then I get a whole bunch of information. Sorry, that's kind of small. But as you can see, it has like a device identifier. And then in the advertisement it was broadcasting, it has some information like, I provide these services, and this is my name. So the app can identify what blenders are relevant for it to use. Going farther down, we can see that it also sent over what service it supports. So there's a few custom services with 128-bit unique identifiers. And farther down, there's a few standard Bluetooth-defined ones like device information that have a 16-bit identifier. Diving into one of these services, we can see that there's a bunch of values called characteristics. And they also have a unique identifier. And they also have properties, such as the ability to read them, write to them, as well as notify, which is basically the server device sends you value changes instead of you having to ask for them. In addition, if it's readable or notifiable, then you'll see a value for that characteristic. If it's writable only, then, well, you're out of luck. And you also have a number of optional descriptors, which one of the primary use cases for them is so your phone can say, hey, I want you to send me notifications or disable sending notifications. So this was enough for me to find out what some of the readable characteristics were, like the scale weight. But for the writable ones, like saying the blend profile, no idea what to choose. So I'll have to get that somehow else. What I ended up with after using that app was a device profile that looked something like this, where I have a list of services and then the nested characteristics that each of those services supports. This hierarchical ordering of information is called GATT, the Generic Attribute Protocol, and is built on top of the Attribute Protocol, which will become relevant later. But essentially, the Attribute Protocol is taking that hierarchical data and then mapping it to a flat table of attributes with 16-bit handles identifying where in the table they are stored. So I want to capture what data is being written to the Blender, so I need a way of intercepting the packets. So the first thing I tried was taking an NRF52 development kit, installing BLE sniffer firmware on it, and then intercepting the wireless transmission between the two devices. And this worked. I was able to capture the packets in Wireshark. However, there are some downsides. Getting all the firmware installed on the sniffer, for the sniffer installed and setting up software on the computer was a bit of a hassle and is a bit finicky in terms of distances between devices when signal gets weak. In addition, you have to buy external hardware, which isn't the greatest. So ideally, I'd like to be able to just take my phone and plug it directly into the computer. So turns out, inside of your phone, it looks something like this. You have the Bluetooth controller, which is talking to the radio and handling low-level aspects of Bluetooth. And then you have the host processor, which runs your application, as well as parts of the Bluetooth stack, like the GATT and attribute protocol layers. And there's communication between them that happens over a link called HCI. Yeah? Oh, thanks. Or the host controller interface. So both Android and iOS let you snoop on the communications happening here. So this is another place we can intercept what's happening. So on iOS, you have to go and get a configuration profile from Apple to install it. But then once you do that, you can then hook it up to your phone using a cable. Using the macOS packet logger software, you can then get all the information it's sending and receiving. So here, I captured the initial connection to the Blender, so I get the list of services and characteristics it advertises. And then after a little bit, once we're connected, I then step through each individual blend setting profile to capture the write request that my phone is sending out. After capturing that information, I can then stop the recording and then go up into the filter menu, select attribute protocol, packets getting sent from the device, and narrow down the list. After narrowing down the list, you can zoom in and see that it has captured the characteristic that's being written to. So this is something I'll need. Now I know what I need to write values to control the Blender. And it tells me what value is written. So I mentioned the attribute protocol before and starting sniffing before connecting to the device. So if you don't do that, then you only get the 16-bit attribute handle. You do not get the characteristic that you need to write to in order to control it. So after getting all these values, I put them into a table like this, and then lay them out with the blend time. And right away, we can see that the standard blend, which is basically just on for 45 seconds, is only 2 bytes. So let's try splitting everything up into 2 bytes and see what it looks like. And we can start to see some patterns emerge. So especially in the second byte, you can see that when it's always on, that's just A0. For the other ones, there's an alternating pattern of A0 bytes mixed with null bytes. So since the blend profile turns on and off, this is likely the motor speed. If we take a closer look at this first byte, if we convert B4 to decimal, we get 180, which is 45 times 4, or the blend time in quarters of a second. To confirm that, we can take the super blend profile, convert the first byte for each of those pairs into decimal as well, add them up, and we get 204, which is the blend time in quarters of a second. So with that, I was able to write a web page using web Bluetooth, and then we can see the blender shows up, connect to it, and then in a moment it will synchronize, and we start getting characteristic values that are readable. You can see that we're getting a scale weight now, and as water gets poured in, we're getting notifications about the weight increasing. Then I add a drop of blue food coloring so it looks a little bit more interesting, hopefully. Take the cup off and prepare it. Yeah, time remaining, you can see it says 45 seconds for the standard blend profile I gave it. And then let's go create a custom profile. Might be hard to read, but the first step is running for 12 quarters of a second, 3 seconds at a slow speed. Then next it's going to run for 3 seconds at a slightly higher speed. Then it will take a 2-second pause before finally going for about 2 seconds at roughly the maximum speed supported. So I can then save the profile to send the packet over to the device. And then you can see time remaining is updated to 10 seconds. And I'll put the cup in and twist it to start the blend cycle. So now it's running for about 3 seconds slow. Now it should speed up here, and it's going to pause in a second, and then full speed for 2 seconds. And now it is done. We have the perfect blend setting for blue water. All right. So this is available on GitHub. If you want to check it out, play around with it. If you happen to have a NutriBullet, you can try it out too. Scan the QR code if you can. Otherwise, github.com/nightlark/NutriBullet. And thank you. You can find me on Discord and social media at rmast.
Alrighty, that is it for that session. We're now moving into unconferencing time. So we've set up an unconferencing board back there. Folks have put up some ideas back there. I am thinking maybe we should move the whiteboard so that it doesn't become crowded. I don't know. There's a whiteboard back there. Unconferencing time is self-organized. There are various places around the courtyard that you can use. And yeah, I think there's some really cool topics over there. Go check it out. Folks are, again, self-organizing. Check it out on Discord. There's an unconferencing channel on Discord. And I think someone also created like a forum-like thing there to help you find cool unconferencing sessions. So enjoy, and anything else?
So unconferencing will go until 4:25 p.m. And we're told that there will be cookies and coffee arriving at 4. So stay tuned for that. And if you're speaking in the session following this one, come up here at around 4:15 or so. All right, enjoy. some water and a cookie, and make your way over to the seats. It's nice and shady over here now. Hooray! All right. Our first speaker of this session works on new ways to program and interact with computers. He made TabFS, a browser extension that turns your browser tabs into virtual files, Screenotate, an augmented screenshot app, and he's worked on physical computing systems at Dynamic Land and Folk Computer. Please welcome Omar Rizwan, who will tell us about how to design your own microchip.
Thank you. Good afternoon. I spoke at the first Bang Bang Con 10 years ago, so it means a lot to be here. I'm really grateful to all the organizers and to everyone. So I'm Omar. I'm going to talk about how to design your own microchip. And I wanted to start by talking a little bit about what a microchip actually is, to try to motivate what exactly the thing we're going to try to design and get manufactured is. So the iconic image of a microchip is this little black rectangular thing, probably sitting on a circuit board, like this green circuit board. You probably think of your CPU, your GPU, maybe your RAM. If you take apart your phone or your laptop, you'll see a ton of these. But it turns out that as I was learning about this, a lot of other stuff is also made with a similar semiconductor photolithography. The same kind of manufacturing process that I'm going to talk about is also used to make the OLED screen on your phone. It's also just a grid of little lights that's manufactured the same way. Solar panels, the radio in your phone is also made the same way. It's also a chip. A camera is also just a grid of little light sensors that's printed on silicon the same way. The motion sensors, even a projector are these little micromechanical things that are also fabricated the same way. So basically all kinds of almost all important technology that you might think of the last few decades is designed this way, drawn and then etched into silicon. So I wanted to learn how to make one. I wanted to learn how to make a microchip, or at least how to design one and get it made. I don't know, for the same reason that I want to know how to make an operating system or a programming language or whatever. I want to know how my computer works. I want to know how one gets made. So these are the chips that I designed and got made. I have one here, which I'll show later. They're in a little bag in my hand. This is one of them. So you can see there's the top side on the left, which is kind of shiny. So you can't, it's inside a package, right? So you can't actually see the circuit, even with a microscope, unless you used acid to burn it off and then looked at it with a microscope. Then you can see the circuits. So there are some people who do that. It's really cool. That's not what we're doing today. And then that actually does look like some of the diagrams I'm going to show. And then there's pins on the bottom, which you can use. They're kind of blurry here, but you can use you use the pins to connect whatever you want to connect the chip to, whether that's a screen or a radio or a mouse or whatever, right? Okay, so how does one get their microchip made? Let's say you have a design. Who do you talk to? Where's the factory? A few years ago, this free program started where Google and a bunch of other people, this chip fab Skywater in Minnesota were like, we want to support more people to learn about chip design, and we want there to be an open source chip design tool set. Kind of like there's open source C compilers or open source, all kinds of other stuff. We want to have the same thing for chip design. So they started this program where if you put your chip design on GitHub, you can get it manufactured for free, which is pretty impressive because traditionally, if you wanted to have a chip design, if you wanted to have a chip made, you would kind of either have to be working at a company that designs chips, or you'd be an electrical engineering grad student, because it's really expensive to make the mask and then fabricate it in silicon. This is probably $10,000 of value of this free program of oh, I'm going to send in my chip for free and get it made. And this process that Skywater is using to make chips is a 180 nanometer process, roughly. So for comparison, the top of the line chip in your iPhone 17 or your M3 Mac or whatever is a 3 nanometer process. So it's a little bit outdated. It's like a GameCube chip or something. It's 60 times the Logic gates are like 60 times bigger. You can kind of think of it as being than in the chip I made than in your iPhone 17. But still, you know, it's a real thing. So 180 nanometer process that we're talking about. This guy, Matt Venn in Spain, set up a course a couple years after this program started, which is what I took. I'm not affiliated with Matt, but I would definitely recommend checking it out if you want to learn about this stuff. He kind of assembled the curriculum and like put all the weird Python and Tickle tools in a virtual machine so you can just like run the command to synthesize your chip design. Yeah, like a lot of the stuff like that. And it's, you know, it's super approachable. Like it's not something you need to have like a ton of hardware background to learn how to do. Okay, so we want to make a chip. We know who to call to get the chip made. What do we actually want the chip to do? Like what is the function that we're going to be trying to implement? So I had done little kind of hardware computer consoles before, so this is kind of what I wanted to do again, like maybe a mouse and a keyboard and a screen. I decided the keyboard was too much work, and I feel like if you can choose between a mouse and a keyboard, the mouse is more interesting than the keyboard. There's kind of a subversive energy to that, because the mouse is like what you use to directly manipulate things. So the system diagram is kind of going to be like Omar's chip, and then like PS2 mouse and VGA screen, and that's what we've got. And you can see, you know, here's where my chip would be, here's the mouse, and here's the screen. So the chip is generating, you know, the white pixels and then the blue pixel. It's storing where the mouse is, and it's generating blue pixels for that, you know, 24 times a second or whatever. How do I design the chip? Do I draw on pen and paper? Do I type it out in Microsoft Word? Do I make a spreadsheet? It turns out that it's surprisingly, at least for digital design, which is like a CPU or GPU or something, it's surprisingly like programming. You write a bunch of code. This is the GitHub repository. It's actually public. You can go look it up. And you write in a hardware description language. So the ones you might have heard of are Verilog, VHDL. There's a bunch of more exotic ones that are probably better, but not used by anyone. And the one I use is called System Verilog. So this is some System Verilog code. It's like kind of a whole new way of thinking. You have to think in terms of like state machines, and it's kind of like functional programming. You draw all these diagrams of state machines and like ring buffers between the different parts of your chip, but I don't have time to talk about that. And now that I have the code for my chip, I need to convert this code description, which is just text, into a CAD file to send to the fab so they can actually manufacture it, like cut it into the silicon. So there's this command, make harden, that I'm going to run. And this is sped up a lot. This took 5 minutes in real life, which is still pretty fast for chip layout. It has to do a bunch of stuff. It has to do synthesis, where it turns my code into a graph of like logic gates and like what logic gates should connect to what other logic gates. And then it has to do placing and routing, where it actually makes the concrete diagram of like, oh, what stuff has to be drawn where, how is it connected? And that's an NP-hard problem, so it's like an optimization problem. You get different results. It can take anywhere between 5 minutes and like 30 hours. If you talk to people in industry, you know, it takes days to just get the layout, let alone to know how it works. Okay, we're done. This is the layout that I got out of hardening my chip design. So one fact that I think is really cool that I didn't realize and really important to emphasize, this is a view from the top. So this is like me looking down on the chip. If you've seen like decap chips or chip diagrams in passing, they usually look kind of like this. But this is not really how the chip actually looks. This is just like looking down. It's just like a planar view. If you look from the side, you realize that microchips actually have layers. And at the bottom layer is where all the logic is, like down at the bottom. And then the upper layers are all like interconnects, so like wires, kind of like on a PCB, like Liz was saying in the previous talk, are wires like connecting different parts of the chip. So when we look at this, we can actually, we can actually take this view and we can zoom in and we can rotate and kind of view it from the side. And you realize that this is actually kind of this whole 3D structure, where at the top you have these blue layers that are like the highways, and then as you go further down, you see that there are layers and layers of like at the bottom, you have like local road, well, at the bottom, very bottom, you have logic, and then you have kind of local roads, and then avenue, and then streets, and then avenues, and then highways at the top. So when you're making a microchip, like all the chips in your computer are really these like 3D city-like structures, which is something I thought was really cool and not what I thought of when I first started this process. Okay. Yeah, so we have our code. So we had our Verilog code. We converted it to a CAD file with this whole 3D structure in it, and then we convert that into a chip. Or we send that to the fab in Minnesota. That's the fab. And then a few months or years later, this guy. Fun fact, I was told that less than 1/3 of what they call a chip tape out, where you send this to the fab, end up working. I have a friend who works for a friend from college who works for a major GPU company who would say that, yeah, you send it in, you get it back, it doesn't work. That's kind of like tens of millions of dollars down the drain. And in practice, I haven't talked about this at all, but you actually spend like half your time testing, or more. Even for this, I spend half my time testing. Probably in practice, in industry, you spend 80% of your time testing. But yeah, thank you all very much.
Thank you, Omar. And as Omar said, he gave a talk at the first ever Bang Bang Con. So bookending the Bang Bang Cons, I love it. Our next speaker is an artist, technologist, and designer based in Brooklyn. His work addresses data, imagery and language processing, and experience design through a blend of web-based projects, video works, and tangible installations. His practice explores unexpected connections embedded in our technocultural landscape and the interactions between humans and machines. He's also a part of Switcheristic Telecommunications, an artist collective duo who we are going to be hearing from tomorrow. But in this talk, we will be hearing from half of Switcheristic Telecommunications, which is Yufeng Zhao, who will tell us about finding random things on the street with full-text search. Let's welcome Yufeng.
Thank you. That was a lengthy bio that I sent to our project application, so that was the wording. Cool. My name is Yufeng. I'm a technologist. Let's find some random things on the street with full-text search, like these one-way signs. So I'll do a live demo right now. I built this little search engine thing based on street views in Brooklyn, New York. And I have some keywords prepared, and feel free to shout out some keywords that you want to see on the street. This is hot sauce. In Brooklyn, if you search hot sauce, you get hot sauce. If you search breakfast, you're going to find some deli, diner, organic restaurant, burgers, smoothies, fresh juices, breakfast. If you search customers only, you're going to find parkings, bathrooms, that's for customers only. Any keywords from the crowd? What is that? Psychic. Wait. We have psychic readings. Okay. So how did I do it? Let me get back to full screen. So in Brooklyn, there are 75,000 one-way signs. Here are a few of them. In Brooklyn, there are 3,500 love found, mostly in Popeye's marketing materials. In Brooklyn, there are 51 matches for best pizza, many of the same stores. How did I do this? It's an intersection of all the things I'm interested in. Shortly after I realized I can download all the street views from Google with a hidden API thing that they had to open to the public because everyone can access Google Street View, I immediately downloaded 300,000 Street View around where I live, which is Brooklyn. Each spot is in 5 meters away from each other, and I just sample all the latitude and longitude in Brooklyn. How? It's this GitHub repo that I'm not going to disclose because I don't want to spoil it. But yeah, it's a few Google search away from getting it. And I think it's fair use Google, but just in case, I'm not talking about how I download it. But extracting tags from Street Views is the main part. So if you download it, if you get a Street View, the typical resolution is going to be 16K by 8K, which is fairly large, and you would think that, yeah, just run an OCR will be enough. But no, first because OCR is pretty slow on image of this size, and second, there are distortions on the text that are closer to the pole, top and down. And how I did it, I take multiple photos, each one of 45 degrees field of view, and then I take 16. I have some overlap between them, so the panning interval is 22.5. So 16 photos of each, and I have a 2,000 pixel by 2,000 pixel for each one. Overlapping is because this case. The Broadway sign is cut between the two Street View photos, and if you don't have something in between, you're going to end up with the Broad and the Dway. And because I'm oversampling, I have a Broadway right in the middle. And from the plain photo OCR result to the text Broadway and the bounding box in the plain image unit is XY with height, but it doesn't work if you want to pinpoint the text on a sphere. So with some trigonometry and camera math, you can figure out where the yaw pitch, the width and height in degree on the sphere the text bounding box is on. So overlap is crucial for preserving the whole phrases, but what about the duplications you get? Because now you have Broad, you have Dway, you have Broadway. I'm still working on this. Duplication remove is a lengthy process. It's a complicated one. I'm using geospatial tools just because I'm lazy on the math. I feed this into GeoPandas on Python and feeding the OCR result as if they are regions on the Earth and let it figure out how much they overlap with each other. And also taking into account of the text distance between each other and finding among a similar text cluster, what's the longest one? I'll take that as the right result. But this is still in progress, so you will see a lot of duplications on the actual websites. So with 300,000 Street Views, a month of nonstop compute on my personal MacBook, because the OCR engine I chose for this task is actually the Mac built-in OCR, which is really good for how fast it is and how accessible it is if you have a Mac. And I ended up with 7 million OCR results, and all on all text plural.nyc. Let's find some random things. I have a few interesting ones prepared for you. This is if you search fuck, you get fuck this bullshit and fuck Putin on the right one, and along that line, free Palestine signs on these two. There are a lot of writings that you can recognize and will be otherwise impossible to search on the internet, on the street. And you can search it with this search engine. If you search for sale, this might be a good use case for buying something. If you search lost dog and lost cat, you will find a few posters. I hope they're found by now. If you search happiness, yeah, you can find happiness on alltext.nyc. If you want to find happiness, you gotta, well, the data set I acquire show a strong correlation between the Rita ice cream store and happiness. So maybe that's the way to go. If you want free stuff, search free. You get free soap at this laundromat at Flatbush, and you get free, well, 99 cents budget parking if you have a car in New York. And you can also find Jesus. This is Jesus' billboard. Behind is the Brooklyn skyline, pretty iconic view, and also Jesus love you on the garbage. So this is the word cloud of all the OCR results. Not surprisingly, you see a lot of one-ways and a lot of stops. New York exit, parking, speed. 30 a.m., 10 a.m. is also quite common. And the Google is from the almost translucent watermark that Google add on to the Street View. So this is a distribution of a few keywords. First, we start with one way. It's more in the most populated areas in Brooklyn. If you search Delhi, Sunset Park show hike. If you search love, Williamsburg, probably because the gentrified storefront like to say love on their marketing materials. Distribution of love is such a playful concept, so I also build like a physical installation as if I'm tracking down on an investigation board where these are. So I printed too many of these photos. If you want one, get one. These says love in the center of these photos. If you want to find best pizza, there are a few best pizza spots. We need a taste test. Because it's New York, the best bagels is really deep in Brooklyn. Like, you need to go really far to get best bagels. And in general, best things in Brooklyn are in these spots. And guess what? They're Best Buys. One of them is permanently closed. So I'm not the only one who thought of OCRing Street View data to map the urban landscape. USC has a lab called Spatial Analysis Lab, SLAB. They have an amazing project called Ethnicity, which maps a lot of street signs in multiple languages in the LA County. Slab.today/cultural map, you will be able to see an interactive map that shows you different ethnicity groups on the LA County. So future plan, scan the whole city. I'm gonna finish it sometime. And I'll have some built-in visualization tools, so stay tuned. All text, plural, .nyc. And maybe you can make your own after this talk, as long as you can get those images in legal ways, of course. So let's find some random things in full text search. Just go to this website, find something. I have my social on the landing page of this website, so feel free to @me on Instagram if you found some weird things. Thank you.
Thank you, Yufeng. BangBangCon got its start in New York and was in New York from 2014 to 2019. So it's only fitting that we would have that talk today at the last BangBangCon. All right, we have one more talk in this session, and our speaker is an Argentinian security researcher and developer who believes that someday engineers will have the right tools and knowledge to build truly secure software. But since that hasn't occurred yet, he simply refuses to use many applications until their security holes get fixed. Matthias Lang will be telling us about blaming physics for our evil actions.
Okay. Let's see if this works. Does that work? Okay, I'll double check. No. Can you see anything? Okay. Oh, it's disconnected. Okay. Let's try to configure this again. Solution. That's weird. Just a sec. Disconnect this. Oh, that's why it didn't work. Wrong connector. What is HDMI? Here.
Hold on a second.
No, I don't want to break anything.
Okay.
Oh, it has the adapter. No.
Or what do you need, HDMI?
That's it.
Okay.
Whoa. Woof. Okay. Okay. Hey, BangBangCon, it's awesome to be here again. Let's talk about RAM memory. As most of you know, memory stores data as bits, zeros or ones. One will expect that if I write a 1 to the memory in certain memory location and then read again, I should get a 1, right? Unfortunately, software runs on top of hardware, and hardware can sometimes fail. One of the reasons of failure is called a single event upset. Single event upsets occur when a certain single particle, such as a cosmic ray, gets close to one of your electronic components and changes the electrical representation of a bit from 0 to 1 or vice versa. Single event upsets can occur at any time. However, there are some conditions that make them more likely to occur. Things such as high altitude, having a device with low energy consumption, or a device that's too old, or maybe a low quality power supply, or just being in a high temperature environment. Let's switch subjects. Oh no, sorry, I forgot. Well, these bit flips can cause some serious struggles in production systems such as a voting machine or even airplanes. Dangerous, right? Now let's change subjects. Let's introduce you to Shia. Shia is a contributor to a well-known piece of software whose maintainer has been kind of burned out this few months. So Shia offered to be in charge of releasing new versions of this software. After that, she realized that maybe she can tamper the contents of the executable files that get shipped to the users, and maybe add some malicious content to them. That will be an interesting supply chain attack, right? Of course, that she doesn't want to be detected. So she can just replace the whole contents of the original file with a totally different malicious executable. She needs to be more clever than that. The other day, she had this revelation that maybe she doesn't need to replace the whole contents of the file, but instead she can just change a tiny part of the original file and then making the resulting binary malicious. Maybe she could just maybe she could just change a single bit of data. Think about that for a moment. Changing a single bit of data is literally the smallest possible change we can make to a binary. So that should be really difficult to detect, right? And even if someone somehow detected this, Shia could, since it's a single bit flip, Shia could just blame the cosmic ray for that. It wasn't me, it was the cosmic rays. Cosmic rays in your laptop, exactly during build time affecting the GCC process and flipping the exact bit that turns our executable file malicious. Yeah, you know, I'm a digital nomad, I travel a lot, so I think this last build was done while flying on an airplane at 30,000 feet. Maybe that caused the bit flip. Or maybe, yeah, I just used an old Raspberry Pi I had and a low quality power supply I found on a dumpster the other day. I built it with that, so maybe that caused the bit flip. Everyone just loves using old Raspberry Pis for production stuff and just pretending that's all right. Yeah. Or maybe, yeah, build time took so long to compile, I needed to do something else. So I just took my machine with me to the kitchen, started preparing some pizza, turned on my 800 degrees pizza baking oven, and maybe that could have caused the bit flip change. Look, my laptop is melted. It wasn't me, it was the cosmic rays. Of course, that for this attack to succeed, Shia will need to find the exact bit that turns the binary from a legit thing to a totally malicious one. This at first looks difficult, right? How can we change a single bit and cause so much damage to a system? Well, let's see that in a second. Let's introduce you to this piece of software some of you may have heard of sometime, called OpenSSH. This is the code. I don't know if you can see, okay? Well, this is the code used by OpenSSH to perform the public key authentication. This call to the SSH key equal function will check that the public key you use to log in is in the host machine's authorized key files. Otherwise, it will reject us. That code gets compiled to the following assembly. Can you see? Right? Okay. That assembly is just an instruction, a call instruction, a test that checks the return value of the function, and a conditional jump. If the function returns 0, that indicates failure. The test EAX will set the 0 flag to 1, and the jump if equal will be executed, and we will be taken to the code that rejects our login, and we won't be able to log in. Let's look at that jump if equal instruction for a second. That instruction gets encoded into x74, right? If we take a look to the x86 opcode table, we can see that by just flipping a single bit, we can transform that jump if equal instruction into a jump if carry. Since the previous instruction was a test instruction always set the carry flag to 0. So if we change the instruction from jump if equal to jump if carry, that means that jump to the code that rejects us won't be executed and will be logged in. Interesting. So, okay, I think we can have a demo. Okay, I have enough time. I think I should do this. Oh, can you see anything? Okay, I can see that. Oh, no, it's like this. Okay, maybe I'll send this. This is the attacker machine. This thing is the server will target. To simulate this attack, the idea is to manually change the contents of the binary file to pretend the supply chain attack existed. This technique could also be used, for example, by an attacker who wants to gain persistent access to a system, to a server, and then gain, to infect the system with this. So, to perform the demo, let's go here, or maybe, okay. If I'm the attacker, and I try to generate an SSH key, of course, since that key is new, I can't just try to log in using that key I just generate with root to a server, right? Of course, I can't do that. Yeah. Okay, let's go to the, okay, were you able to see? Okay, right. Okay, this is the target server. Let's stop the SSH binary and perform some hexadecimal addition. Okay, 2, 4, 6. 2, 4. In this position, there's that 74, if you remember, that's a jump if equal. Let's change that to a jump if carry, as we saw. Let's start the service again, and if everything works properly, woohoo! Thanks. Built by the cosmic rays. Just a sec, okay. So, just to finish the session, let's have some conclusions. First, if you are developing some security-sensitive software, please invest on ECC memory. That's error-correcting code memory. That should fix most of the issues we show here. But second, and most important, if we want to take security seriously, we must take supply chain attacks into consideration. And if we want to prevent the supply chain attacks, we must have bit-for-bit reproducible builds. that will enable us to detect any inconsistencies in the build time and prevent this and many other attacks. So that's the main takeaway I want you to get with. Reproducible binaries and bit for bit reproducible. Thanks. Oh, well, I didn't show my ID, but that's okay. Well, you can reach me out later.
Thank you, Matthias. That was badass. Can we get one more round of applause for all of today's speakers, please? So we have come to the end of the first day of the last Bang Bang Con, and I have a few announcements to wrap up the day. First of all, these things, they're yours to keep. You don't need to return them. They are actually the swag that we have for you this year to take home. So please, take one. If you didn't grab one before, you can get one on the way out. There's more of them over there. And we have even more boxes of them if the pile on the table isn't enough. So please, take your official Bang Bang Con butt pad. I have a couple more announcements. One is that we have a few suggestions up there on the unconferencing board for places that people might like to go to dinner, as Sarah is indicating right now. So those are just a few suggestions that the organizers had, but it's by no means the only places you can go. And we thought people might like to self-organize into dinner groups. So if you'd like, you can go up to the unconferencing board and maybe put your name next to a place that you might want to go, and other people might want to sign up for that place as well, and then find some fun people to have dinner with. Other announcements, let's see. What else am I supposed to say? Oh, yes. If you have time to hang around here and help us put away chairs and that kind of thing, we would love some help. So for anybody who does happen to have time, hang out for a little bit and we'll try to figure out how to efficiently get the work done. Is there anything I'm missing, other organizers? Going once, going twice. Okay. All right, thank you everyone again. Let's have one more round of applause for all of today's speakers. Oh, here comes Sarah with trash, yes. Okay, so there's all these trash bins over here. There's trash recycling bins to my right, I guess stage left. If you see any trash around on the ground, let's try to throw it away before we leave. Thank you.